Hello, can you hear me?
Yes, we hear you.
Thank you. So we'll wait a little bit more for speakers. Adriano, did you test the slides? Do you want to give a try?
Yeah, maybe I can give it a try. Hi.
Okay. I can
Do you see my screen?
Yeah.
And do you see the video?
Sure. Running.
Okay, perfect. Okay. Now you can also see me.
So while we wait for the speakers, just let me tell you a few things. Okay, first of all, remind you that apart from the talks of these sessions, these all sessions, we have some additional content on the webpage. And let me show you a few examples. So for now, for example, we have these two editions by Jonathan Bares and Ilya Zaliapin. And I can show you here in the webpage, you can find these contributions here and the section, for example, or contributions. You can go there and good luck finding the new ones here. Crackling around the jamming transition, for example, you can go here, have the abstract, and then you can download here all the material, right? So just these two contributions. Ilya is from University of Nevada, Reno. He is presenting some study on the metrics underlying the correlations between earthquakes. And Jonathan, he's from the University of Montpellier. Both will talk tomorrow, so you'll have plenty of time to ask to them anything. And so he's added this contribution, including some insights on frictional sliding, both from discrete element modeling and experiments. I remind you that we have also uploaded the videos here in the news section. You will find all the recordings for now. Okay, so you have the first session already edited a little bit, and then session 2 split between Red Achille's contribution and Ezequiel Ferrero as well. Okay, so now let me see, we have okay, we still have some people missing. So let me just give a few teasing of these new sessions that, well, these 4 sessions that we are starting now, that it's the second part of the workshop. And just let me explain the kind of problems that we're addressing now, that it's the modeling of avalanches and failure from first principles. So we know that deformation and failure emerges a collective effect from the interactions of microscopic particles or smaller constituting elements. And depending on the kind of system that we're trying to model, and as well on our background, we take different approaches to model these processes. So traditionally, we can distinguish between discrete element models approach, which considers a Lagrangian molecular or particle dynamical simulations, or finite element models, which basically what they do is to coarse grain the system into representative volume elements, and that include either Eulerian or Lagrangian dynamics. And apart from that, or beyond those approaches, some features are well captured with very simple conceptual models, such as a mean field framework that you may be familiarized, and these short-range interactive systems for stick slip and fractal dynamics as well. So we'll try to find out here which are the limitations and advantages of these particular approaches to modeling, and we want to have a special focus as well on this. Sorry, if we go here, this fourth section here that was to study if it's possible to study to reproduce these mechanisms that could potentially improve our forecasting abilities, such as correlations, precursors, and the detection of internal details that are captured with these heterogeneities. Right, so just to give fast teaser of the kind of talks that we'll have today and tomorrow. I apologize if I misread some of the details on the abstract, but basically we'll start with Chen Liu from the École Normale Supérieure of Paris. We'll present the modeling approach coupling both mesoscale and microscale to simulate amorphous solids. And Lucas Gehring from the School of Science and Technology of Nottingham Trent University will show us the results in another modeling approach using discrete element models and experiments as analogs to describe cohesive granular media, such as different rocks, such as sandstones and concrete. And finally today, Adriano Gualandi of the Istituto Nazionale di Geofisica e Vulcanologia of Rome will cover, I think, almost all the topics of the workshop in the field of seismology, based on I think it's a rather new technique based on precision geodetic imaging and use Bayesian techniques to discriminate the origin of earthquakes. This evening in Europe, morning in America, Kamran Karimi from the University of Calgary will talk about the role of frictional interactions in the emergence of fracture-like formations. I think he's working with discrete element model simulations as well. He will explain in more details. And finally, Mehdi Poroga from Carleton University in Ottawa will introduce us to some of these new ideas regarding the stability of granular matter based on the internal configurations that can be traced back in discrete element model simulations. And finally, tomorrow at Europe time, so at 2 p.m. Central European time, Swamya Biswas from the SRM University in Andhra Pradesh will talk about scale-free behaviors and resolution effects in minimal threshold models, so one of these conceptual modeling approach, and that, among other things, serve to simulate earthquakes or understand better the kind of recordings that we can do with earthquakes. And Silvia Bonfanti from the University of Milano will talk as well about discrete element model simulations of amorphous silica. And that's quite interesting because they observe two different kinds of elementary plastic events at the same time. And finally, Jean-Paul Ampuero from the University of Côte d'Azur in Nice will talk about the mechanics of earthquakes, and in particular on the origin of faulting through pulse-like rupturing in damaged fault zones. I hope this more or less summarizes the thoughts. I hope I didn't misread anything. So if I think Shen Liu is already here. Shen, if you want to share your screen and we can start this session. Okay. Shen, can you hear?
Yeah. Yes, I'm here.
Okay.
Yes. So now I'm sharing my screen.
Yeah.
Okay.
Okay, so Shen Liu will talk about the mesoscopic elastoplastic model and the rheology of soft amorphous materials. So whenever you're ready.
Okay. Thank you for giving me this opportunity to present our recent work together with Suman, Pinagi, and Kistan on our development of the mesoscopic elastoplastic model to describe the rheology of soft amorphous materials. So let me first introduce. Sorry, how to change slides? I have some problems. Oh, okay, cool. So let me first just talk about our general ideas and the motivations behind this work. So we're interested in the kind of material that we call soft amorphous materials, which admit yield stress or yield strain, below which the system behaves elastically, and above which the system flows instead of a fracture. And we are most interested in the flow part, the rheological behavior of these systems, namely how does this system reply to an external loading. So typically when you shear the system, there is a macroscopic shear strain associated with a macroscopic stress. And there are typically basically two types of experimental protocols. The one is that you control the stress, where you just set the stress to the value that you want and study its response in the deformation. Or vice versa, we can control the strain and to study the response in stress. And then I'm going to introduce our current understanding or knowledge about the plasticity of this kind of a material on the mesoscopic scale. So this is the work originated by Aragon in the mid-70s, which is called the local plastic events. So for example, if you take a foam system, you shear in this direction indicated by the blue arrows. What happens is that you can see during the video that the macroscopic deformation is updated by the very localized rearrangement of particles, which we call plastic events. And this events happens in typical size, I will call it a coarse-grained land scale. And this has been extensively studied and shown that around each of these plastic events, the stress around it is perturbed in some way, which can be described by the H-Lobis propagator. So it's in a 2D, it looks like this. It's not isotropic, it has two strong axes where the stress is enhanced, and then two weak axes where stress is lowered. So this is two basic ingredients of the elastoplastic model. And let me formulate it in a more general way. So we have a description of the local stress perturbation due to the plastic deformation over all space, which is just the integral over all the effect of all the plastic events. And the local stress at arbitrary position can be decomposed into the stress due to plastic deformations and homogeneous external loading. So this is the two basic ingredients that is the same for all kinds of elastoplastic model. But then there's a third part, which is very important, is customer right closure, which related the local plastic strain rate to the local stress. And this is the most variant part if you look across the literature in elastoplastic model approach of the rheology of amorphous materials. Okay, so this is the main part that I'm going to talk about. So with this framework, how to imply different driving protocols in imposing stress, you just set the external loading to the stress you want. If you want to impose a constant shear rate, you add an extra dynamics on the stress, on the macroscopic stress, which works like a feedback loop that you imply the stress in such a way that the macroscopic shear rate is a constant. And then, so this model has achieved several successes in describing the rheology of soft materials. So here are several examples. First one is the description of the flow of colloidal system through a microchannel given different pressure gradient. So in this figure, it plots the velocity profile as the position across the microchannel. So the red crosses are the experimental data, and the blue circles and lines is the prediction from the mesoscopic model. And you can see that it's quite a good agreement there. The second example is an indentation experiment when you press with a small rounded surface to a amorphous material. And this picture shows the patterns of strain localizations in experiment, and which can be actually somehow well captured by elastoplastic model also. In third example is a creep dynamics, where you apply a step stress onto the system. And you can see the response in strain. When you apply small stress, the system just stuck somewhere. And when you increase the stress, the system will eventually flow, and the long time limit, the strain increases linearly with the time. And this is also, so the left is experimental results on some kind of suspension, and on the right is what we produced with the plastic model. The last one is the recent study on the transient behavior that depends on actually on the thermal history of the preparation of the samples. So here you see that as the sample is equilibrated at different temperatures, the overshoot will depend on this temperature. So this is also can be reasonably captured by the model. But on the other hand, we have some critiques on the elastoplastic model. So the major one is that the elastoplastic model is quite phenomenological. There's we don't know how to derive these things from the first principle. And also that with respect to each problem, for example, in the slide that I showed before, we changed the settings of the closure, and we changed the parameters to fit the different phenomena. So people can create critiques that it just reproduce what it behaves in real life, but that doesn't make progress in understanding. So with these critics and successes, we have questions that rise from a scientific point of view. The first question is that what are the two ingredients, namely the localized plastic events and the interaction kernels, are sufficient for which kind of problem? So for which kind of a problem these two ingredients are enough? So this is completely not clear. And then what is the relation between the gradient inside the model and to first principles from a microscopic point of view? And from an engineering point of view, so we would like to ask what could the elastoplastic model be the basis to develop a material specified description? So more practically is that can we actually build up a setting of the closure and some parameters that allows us to obtain the mechanical rheological behavior of a specific system once for all, and that we can obtain these rheological behaviors only by solving the models under certain loading condition. So this is the main question that we want to attack during this work, and answering this question will also help to answer the question from a scientific point of view. So this is our task. So how do we do that? First, we have to choose a particular amorphous material. So the material that we choose is a microscopic model of real amorphous materials. It's a 2D binary linear Jones system with a system size that we can achieve to the best. And what we do with these systems? We prepare, so we first equilibrate the system at the temperature that is slightly above the mod coupling temperature, which we are sure that system is in thermal equilibrium. Then we quench the system to T equal to 0 at different weights to obtain different samples of different stabilities. And to each sample, we apply two protocols, two driving protocols, which is orthogonal. The first one, we control the shear rate. This is the shear startup experiment. Then the second one is that we control the stress, which is the creep. And we focus on two types of observables. The first one is steady state observable, the flow curves in both driving protocols. And the second one is we also want to match our mesoscopic model to the transient process within these two driving protocols. Namely, for the shear startup, it's the stress strain curve, and in the creep curve, it's the time series of the shear rate. So how do we do that? Let me just first recall that the elastoplast model in its general form can be written this way, where the local shear rate is related to local stress with unknown function that we want to determine or we want to search. And we apply the two driving protocols through the way that I talked about before. So with respect to the observables that we want to match, so
We're losing the video and audio. Jen. Hello? Now we get the screen, but we cannot hear, not see you. I think we've lost the speaker. I don't know if he's on the. Okay.
Hello.
Here. Okay.
Okay.
Now, okay. Yeah, we lost
Thank
you when you were.
Yes, I think the internet has a problem. So where was I?
You were on the slide regarding the limitations of. So you were summarizing all the EPM model approach, right? And
This one?
We cannot see it right now.
Sorry. Share my screen. Can you see?
Next one.
Okay.
I think it's to.
This one?
No, I think it's the next one. Next one. No, it was the next one. Sorry. Here. You were around. Yeah. Yes.
Okay, so this slide. Okay, so I continue. So this slide is just to say that which kind of criteria is to follow to search the unknown closure, the function of x. So basically, with respect to steady state observables, we want a natural steady state of this dynamics produce the correct flow curve. And with respect to the transient process, you want this f takes the initial condition that depends on the thermal history and reproduce the correct transient behavior. Okay, so after a lot of tests, a lot of work, we find a kind of disclosure that does reasonably good this job. So the disclosure is written in this way. So it's quite simple. The local shear rate is just linearly coupled with the local stress, but we introduced the local state variable that alternate in between 0 and 1. When it's 0, when it means that locally there's no plastic events, and when it is 1, the local plastic events takes place. And so it the local plastic events activated when the local stress is larger than certain thresholds, and with a typical rate, with a rate of typical time scale that they call tau plastic, and it can become elastic from plastic state as a rate of a typical time tau reconstruction. And once it returns to zero, a new random local threshold is drawn from a distribution. And we choose this distribution to be a Weibull distribution for the reason that in the literature it's already measured also in our work that actually this local thresholds can be reasonably described by a Weibull distribution. And then we have at the end to choose a mesh size of the elastoplastic model to actually that actually corresponds to the actual size of our molecular dynamics system. And that gives the cost-graining landscape. So to summarize, we have these parameters. So there are quite a lot. The first one is the shear modulus. The second one is the time scale that fixed the local the local viscosity when there's a plastic event. And these two time scales fix the stochastic rows of the local state. And these two parameters fix the shape of the random, the distribution for the random local threshold that we draw from. And at the end, there's the cost-graining length scale that can be defined as the linear size of the system counted in the number of diameters of particles divided by the length scale, so the size of the mesh size of the meso model. And this is a dynamic system well defined, and then we should inject the initial condition to run the dynamics, which is just the initial field of stress, local stress, and then the initial field of local thresholds, which can be directly measured from the MD system with a certain given length scale. So just a remark before I proceed. In principle, the shear modulus should depend also on the on time, because at time zero the system is just after quench. The shear modulus should be that of the system that just after quench, so that it's a value that depends on the thermal history, and after the system is driven. At the long time limit, the system enters to stationary state. It should converge to a value that is independent on the thermal history. So there's a missing part of the dynamics of the shear modulus, but we have the model has an advantage is that the stationary behavior of the model within the range of validity is independent on the shear modulus. And the range of validity in terms of shear rate is from 0 to a crossover shear rate, where the crossover shear rate is inversely dependent on the shear modulus. So for simplicity, we set once for all the shear modulus equal to its initial value, and then also for producing the correct transient behavior. So then we are left with the question how to fix all the parameters. There's no smart way, but there's several guidelines. So the first point is that the initial shear modulus and the viscosity can be actually measured from the MD system, which is easy to do. Second one, the other parameters can be separated in two groups. The first group is these 4 parameters that control the stationary state, also the transient process. And the last parameter, the cost-graining length scale, will not affect the stationary state properties. It only influence the measurement of initial conditions, so that the transient process. So with these guidelines, we have the first results of fitting the flow curves. As you can see, for different, so for two samples that has two different thermal histories, their initial value of shear stress are quite different. For this one, it has a larger value than the one that has a faster quench rate. And you can see So the results for meso model, namely the triangle and the orange cross, are always the same parameters, only with the mu different. Which you can see that is in the small shear rate regime, the meso model agrees quite well with the molecular dynamics simulation results. And only at high shear rate, the two flow curves deviate from the one of the molecular dynamics results. And the green triangle one deviates a bit earlier than the other because its shear modulus is larger. So with these parameters, we have the first results. So this is the full results of the stationary state. We measured the flow curve from meso model from MD with the two type of sharing protocols, and the all lines on the same line. They agree quite well with each other. And we also measure the stationary state apparent distribution of local thresholds, which is the gamma y here, sigma y here, and also the distribution of the distance from local stress to the thresholds for two different shear rates. The MD data is shown by the detached curves, and the meso data is shown by the solid curves. So they are not perfect in this scene, but they're comparable. And it seems that the meso model has a systematic deviation to the smaller values of these quantities in distribution. And this could be actually rationalized by the fact that in the MD simulation, the MD models, the way that we measure local EO stress is not perfect. Because of technical issues, the values of local stress can actually be overestimated a little bit. And then I turn to the results of transient dynamics. First, I will talk about shear startup experiment. So firstly, by matching the meso data to the MD data, we can actually fix the correct coarse graining length scale. So in this figure on the left, the detached lines is the MD data during the shear startup. And the different colors, the solid lines corresponds to the meso model that with a different mesh size. As you can see, as you can see that only the purple one that matches relatively well to the MD data. And this is due to the fact that when you have a smaller coarse graining length scale, the local stress is much more overestimated. And if you have a very large coarse graining length scale, what you measured as the local threshold is basically you're sampling the weakest one. So only with a reasonable coarse graining length scale, you can produce a reasonable, correct transient behavior in the shear startup. And it's worth to note that also this value of coarse graining length scale is consistent with previous studies of the typical size of clusters of particles that undergoes plastic events. And then we apply this coarse graining length scales to different samples with different thermal histories. So from left, so this one with the slowest cooling rate that we have, and to this one we have the fastest cooling rate. And you can see for different shear rates, the MD data, the meso data actually captures relatively well the transient behavior up to the stationary plateau. And then what is quite surprising to us when we do the work is that once we fix the parameters for the stationary state for the transient behavior of shear startup, the creep curves is automatically fixed also. So here in the first figure, I show the shear rate as function of time when you apply different step stresses to the same sample. On the second figure is the creep curve for the same applied stress, but for different cooling rates. And you can see that within some fluctuations, the meso model captures a relatively good, the MD data. Okay, and then I arrive to conclude. So to answer, so the question that we start is the question that we start. So at the end, we actually find such a scheme of elastoplastic model and a set of parameters that allows us to map in a simple geometry the meso model to the particular material that we choose. And then we also use, from this work, we also validate some hypotheses that has been introduced in the literature that actually the local thresholds is important and useful in describing rheology of soft glassy materials. And we also confirmed the important roles of the sample preparation actually in the transient dynamics, and also what we suggest is that the local, so the initial stress field and the initial field of thresholds actually encoded relevant information of sample preparation to the rheology afterwards. And also we think that we made a first step, or one step, let's say, to develop more accurate material-specified mesoscopic descriptions. And then at the end, some perspectives. So to account for more complex geometrical situations, we need to develop a tensorial version of the model. Okay, and secondly, as I mentioned before, there's a missing part of the dynamics of the shear modulus. How does it depend on the rheological behavior, the history? And this will definitely enhance the model if we study more on this. And at the end, one would, because during this work, we still measure the initial condition from the material and inject it into the model. So one may expect that to develop a theory that is related to the initial condition to the thermal history of the sample preparation. And also so this is what we do here is with MD system, where we can measure local stress very easily, but in experiments, one could expect that in the future, maybe we can develop more method to measure local stress or local quantities to feed the mesoscopic model to provide a prediction of the real system. So that's my presentation. Thank you for your attention.
Thank you, Chen. You can leave your questions in the chat now, or you want just say, I have a question, and then we'll pass the mic to you. Anyway, Chen, there is something that was a little bit confusing for me. So when you apply this thresholding, it only has effect on the first part on the transient, or it affects all? I mean, it's stationary, right?
Which one?
When you introduce the thresholds at the
which slides?
Much earlier.
Much
earlier here. Okay. Yeah.
Yeah.
Okay.
Yes.
So you're considering that the when threshold is overcome, then it flows, or it's just I mean, it plays another role after you have the flow, or it just
sorry, I didn't understand your question.
I mean, you use this Bible distribution.
Yeah.
For the threshold.
Yeah, this is the Weibull distribution. So this distribution is used for once you have a plastic events, you should renew your local threshold.
Oh, okay, new
yeah,
one.
Yeah, the new one. So, but in the beginning, for having the transient, we inject what we measured from MD.
Okay.
Yeah.
So we have another question by Cameron. Cameron?
Yeah.
Cameron?
Hi.
Hi.
Yeah. Hi, Chen. Thanks for the interesting talk.
Hi. Thanks.
So my question is, I mean, you can actually read my question. So how robust are you? I mean, the comparison you made between like the elastoplastic model and like an MD system. How robust is it with respect to a change like in polydispersity or area fraction or interaction model?
No, we didn't try different type of systems. So we didn't change we didn't change the interaction potential of the particles. We didn't change the polydispersity. What I would suppose is that if you change this, we should also change some of the rules of the model to match a new system. The point here is that we can actually, for each kind of material, you can come up with a set of settings of the model that that the model can reproduce what the actual material behaves.
But you cannot add new ingredients. Like you just have to play with like the perhaps distribution of the thresholds. Or
yes, yeah. I mean, in principle, you can change everything here, right? Yeah. You can change even not instantaneous linear coupling, but a linear response, or I don't know, maybe you can change more sophisticated roles for the state variable or another form of the threshold. You can do a lot of things.
Thank you.
Yeah.
Okay, thank you, Chen, again.
Okay, thank you.
So the next talk will be by Lucas Gering.
Hello. Yeah.
Hello.
Can you hear me?
Here. Can you share your slides?
Yep.
Let's see if it works.
Yeah, we don't. Zoom is one of the newer systems to maybe use different systems at my university. So is that working? Do you see the?
Yes. You see your screen?
And for some reason, I still see Chen, but that's fine.
Perfect.
That's
Thank you, Lucas.
all right. Yeah. So thank you, Jordi, for the invitation here. Yeah, so this is work that is in spirits somewhat similar to the previous talk and some of the talks we saw yesterday. And the idea here is we've been working for some time on cohesive materials. These are granular materials where there are bonds between them, and these bonds are fragile and they can break. And we're looking at how these kind of materials distort. And this started as an experimental project, and we're developing DEM models from these, which are informed at every step of the process by direct experimental observations. And we're trying to upscale those to show what we need to put into the microscopic model in order to accurately predict macroscopic behavior. This is work that's been going on for about 5 years. The postdoc who started it, Arnaud, is now a beamline scientist at Soleil. Shomo is at this conference here. He's now an assistant professor at Amaravati, SRM Amaravati. And the numerical modeling has been done largely by Yuta Yamaguchi, who is a PhD student at the University of Tokyo under supervision of Takahiro Hatano, who has moved since to Osaka University. Matthias Schroeder was also involved in some of the X-ray imaging systems, so you might have seen his name. Alexander Schmeich was a very good master's student who did some of the work as well. So I'll start off with a description of what I mean by a cohesive granular material. And I will explain the experimental system that we have at play and what I mean by this having a tunable property. So this is a system, it's a toy model of a granular cohesive system where there are solid bonds between the particles. And it's one that's reproducible in the lab, it's reliable, it's something where we can change a property and see how it modifies the behavior. And then I'm going to show you microscopic experiments. We're going to look at the stiffness of individual bonds. And from those experiments, I will pull back and explain and use those to inform a DEM model which we then perform the same types of numerical experiments as we do compressional experiments, and look and compare the two systems. So this is inspired by materials like snow or sandstone in particular. Snow being a cohesive material which has a high porosity. It's got a low amount of material. Sandstone has a low porosity, but the two systems are related to grains held together by some sort of a matrix material. However, it can also apply to things like soils, and so landslides and soils, or my background is originally from colloidal materials, soft matter physics, so it can relate to the failure conditions of colloids and sols. As I said, the sort of end members from my intuitive grasp of these are things like avalanches in snowpack, which has a low density of material. They're highly porous, and the grains of snow are held together by sort of small bridges of sintered material, basically the same kind of ice holding them together. On the other hand, on the other extreme case, we have sandstones. Porosity there might be of order 10%. And those are held together by some sort of a cement or matrix material. The key physics here is that we have grains held together by some sort of material, which is fragile. And so the contacts, if they break, will not reform, or at least not on the time scales where we look at the dynamics of how these materials deform to failure. Under creep-like conditions, this might be a different case. But the physics we're looking at assumes that the failure and deformations are rapid compared to reforming any kinds of bonds. So we've looked at these in the lab, and we've looked at these with a variety of techniques. The standard experiment consists of making a packing of material like the one on the image on the left here. We can do X-ray tomography experiments of those. We can identify the positions of every particle, every grain, and we can do uniaxial compression tests of those. If we look at the microstructure, the texture of this, it consists of relatively monodisperse grains of glass beads, and we've held them together by plastic bridges. And so that's the essence of this, is that we characterize the bridges, characterize the beads, the strength of the bridges, and the properties of the macroscopic system as a whole. And the question then is, what do we need to tell someone who's building a DEM in order to actually have them be able to predict the macroscopic behavior? So the material itself is relatively straightforward. So most people will have played around on a beach sand, built a sandcastle, something like that. And you don't need a particular recipe to build a sandcastle. Sand, if you get it wet, is held together by bridges of water between them, little capillary bridges of water. And those capillary bridges are basically the same once you add a few % of water. The liquid goes into a ring or bridge of material between the grains of sand. And that lends the sand a bit of cohesion. And in our case, we're mimicking the same kind of materials. We have glass beads. Instead of water, we're using a liquid, which is a curable polymer. So it's something which starts out as a liquid, but when you heat it up, it will solidify. So we mix these things together. We then put it in an oven, and we have something which is like a sandcastle, but rigidly held in place by bonds between them. A recipe of that is basically we take glass beads. They can be anything from the range that seems to work well is about 50 microns to millimetric beads. We can use polydisperse systems or not. They need to be clean in order to have good bonding to the PDMS. But we take a pile of beads, we add a few % of a liquid polymer. We can adjust the stiffness of the whole system by changing the stiffness of the polymer, by adjusting the amount of cross-linking agent that we add to that. More cross-linking agent means that the polymer is harder, less means it's softer. We can also adjust the amount of polymer that we add to make the system have larger bridges, larger bonds between the particles, more cement, more matrix, whatever you want to call it, or less. This is something which is moldable. It has this sort of feel of cookie dough, and you can mold it into whatever shape you want. You can then bake it in the oven, again, like cookie dough, and you're left with something rigid. And then we take those kind of materials and we fail them in various ways. So these are an example. These are some pictures of what the material looks like under different conditions. On the left, we have an X-ray tomogram sample where we've identified the locations by some thresholding technique and identified the Voronoi cells. Sorry, I'm getting an internet unstable. If Jordi, are things going well, or am I breaking up here?
We are hearing you, sometimes a little bit, just shortcuts.
Okay. All right. Yeah, you might have seen the message too, but if things are stable, that's okay.
Because if
Okay.
you think that it's not working well enough, the connection, maybe you can turn off the camera and then we will hear you better.
I'm not sure exactly how to do that. As I said, I'm not that familiar with, try that.
Yeah, like this.
Okay, cool. All right, so, and I need to make that go away. Bye-bye. Will it leave? Maybe, maybe not. There we go. Yeah. Sorry. All right. Yeah, so these are just some pictures of it at different length scales. And you can see that the material looks like what you would expect if you had 2 grains of sand that were wet, that the water would go to a bond between them, and instead of being something wet, these are now solidified into place. If you tear them apart, they won't reform. And so this is a material that we call a tunable cohesive granular material because we can set the stiffness of the entire particle assembly by playing with the particle-particle contacts. So the main things we have to control are the size of the bridges by adding more or less polymer, the cross-linking of the bridges, which changes the elasticity of it. We can also play with the bead size and to a much lesser degree the packing. It's really hard to make any packing with this that's not something close to random close packed, something about in the high 50s, low 60%. And the material has the benefit of being relatively homogeneous, easy to prepare, and very reproducible. So we can take these materials, we can put them in a uniaxial compression cell, and we built a cell that we can put in an X-ray tomograph rig so that we can image it while it's being compressed. Details of that were published in 2016, the first paper in this series. And so with that, we can measure the stress strain curve. We find the material behaves with a very high yield strain of order 0.1, so it can deform sort of 5 to 10%, typically 8 or 9% before failure occurs. The systems, as we made them in the lab, tend to fail by developing a shear band, so a brittle failure mode with a shear band at around that percent. We can then measure the Young's modulus. It looks like a linear elastic material for much of its compression until failure. And we can compare that Young's modulus to the modulus, for example, of the polymer that we add. And if we make that polymer stiffer or softer, we find that the Young's modulus of the cohesive assembly, remember the polymer is only a few percent in the plot here, 2 or 3% of the whole system, that polymer dominates the elasticity of the system. The polymer determines the springs between the particles, which determines the elasticity of the assembly. We can also change the amount of polymer, and we find the interpretation of the data is that the cross-sectional area of the bridges is what determines the elasticity of the assembly. So if the bridges are cover twice the area, they're twice as stiff, and so the system is twice as hard. We find that works until, if you know anything about sort of wetting conditions, there's a transition between what's known as a pendular, where you have rings of liquid between particles, to a funicular state where liquid will start going into the pores between particles. Above that state, the physics is different. We can also do fracture tests. So the second paper in the series was measuring the fracture properties of this. And we find, again, those are tunable. So we can do these with standard test samples. In this case, it's under tension rather than compression. But the failure mechanisms are similarly brittle. It develops a fracture. What we find is the fracture propagates by the bonds peeling off or losing cohesion with the particles. And we can characterize that by Griffith-led condition, where there's a fracture energy associated with the area of the bonds. Again, if we make more area of the bonds, we make them larger, the fracture toughness goes up and the amount of energy to peel them off goes up. That's the interpretation of this, of the plots here, the measurements that we make, is that there's a fixed fracture energy associated with breaking the bonds, which corresponds to a fracture toughness or Griffith condition for fracture propagation. Okay, so this is a summary of the experimental side of things. We've made a tunable cohesive granular material. This consists of hard particles held together by softer bridges. And the elasticity of this is dominated by the bridges and scales with the cross-sectional area and the stiffness of the material made of those bridges. And we have failure occurring, which we can relate to a fracture energy. And that fracture energy is the energy it takes to peel the bridges off of the particles. So that describes the macroscopic properties of the system. Now, if we want to look at how these properties are derived, we can look at individual particles and individual bridges. This is work that we have a preprint for. It's not quite on archive yet, but if anyone's interested, let me know by email and I can send it to you. We should be, it's nearly ready, this part. So the idea here is that we're trying to look at what are the microscopic modes of deformation that we need to consider and we need to put into a model in order to reproduce the macroscopic behavior. So you can imagine multiple different types of deformation of two particles interacting with each other. On the left, going from the left to the right, we can have direct compression, we can have shear, or we can have various kinds of torques or rotations. And we're going to focus on the translational modes here, where we squish two particles together or we shear them directly across from each other. The torsional mode of two particles twisting, we don't think is being activated based on sort of some of the way we interpret the X-ray tomogram experiments. And the rotational mode is present, but we are going to assume that much of the properties there can be decomposed into translational modes. So we're not going to look at the rolling as much. So from these, the two on the left are the ones we're going to consider. And we made some experimental tests with a micromechanical sort of testing rig. This consists of gluing taking one of our materials apart until we have only a very small fraction of it, which consists of two particles held together by a bridge. Gluing that particle assembly to a very tiny pipette, micropipette, and then under a microscope, stretching that pipette until we can see the deformation. This is something that's, it's a micromechanical testing rig, basically. So if we look at what happens there, we have the two beads and they will be pulling apart from each other. And I'll start the movie going. By measuring the displacement of the various objects in the image, we can measure a displacement between the beads by fitting circles to them. And we can also measure how much the micropipette has moved. We know it's spring constant because we've calibrated against a hard surface. And so we can measure a spring constant of the bond. So just to play again, we have experiments where we take a single bond between the particles, we stretch it, we can measure its stiffness, we can measure when it breaks as well. So we can measure a spring constant for those bonds. We can do the same thing in shear. This movie is a lot more boring because we don't stretch it until failure, but you should be able to see the particles moving against each other before and after. What we find is that the shear spring constant, the shear mode, is much softer than the normal mode. So if you look at the shear stiffness, it's of order 10 newtons per meter. The normal stiffness is of order 100 to 1,000 newtons per meter. There's quite a lot of scatter in the data, but if we try to do the same thing with a COMSOL simulation of the geometry of two round particles connected together with a blob of polymer between them, we find comparable results because we know the stiffness of the polymer, assuming that there is a small gap between the beads of about 1 to 2 microns. and the results are a bit variable depending on how large that gap is. This is consistent with particles that might be slightly rough, for example, or where there's a bit of a wetting surface between the particles. So the key result here is that we have a stiffness of the particles, or the stiffness of the bonds between the particles, that we can then give to our numerical model. So the numerical model is something that it's a standard discrete element model. We take particles, these are inspired by the models designed for granular materials, except we play with the force law for interacting particles. We have a case where there is a bridge between particles, and we have a case where that bridge is broken. And we have a failure criterion where a bridge will fail, which is based on an energy-based criterion, or Griffith criterion, where we know the adhesion energy or interfacial energy corresponding with peeling those beads apart from each other. That comes from our fracture toughness measurements. So in this model, basically every component of the model, including in some cases the particle positions, because we have X-ray tomogram data, is derived from a matched experiment. These results were recently accepted last week to PRE. There is a preprint on the archive as well of that material. So we can take these simulations. This is one at a high volume fraction, so that it's crystallized a little bit near the boundaries, and we can compress those. And they will fail like the experiments do by shear failure, shear band formation. These are two experimental stress strain curves to show that the comparison between them. The experiments on the top, the simulations using the same material properties and the same coordinates of the particles are on the bottom. We find that pretty much everything works the same way, with the exception that the simulations are about twice as stiff. We attribute this to the fact that in the simulations, we're making all the bonds of the same stiffness, whereas in the experiments, we know that if particles are a little bit further apart, the bonds between them will have a lower spring constant. So we're not taking that variability into account. And that's what we believe is making the difference in the little sort of factor of 2 between the stiffnesses. I'm not going to talk about it because of lack of time, but the gray area, the gray bars at the bottom of the numerical results are the activity, and that shows the type of failure. So there may be some questions about that related to some of the things presented yesterday. Happy to talk about that more. If we put this in, we have spring constants that are derived from a gap of 1 or 2 microns. Those give slightly different possible choices of the spring constants in the numerical model. And we can compare the results to the measured Young's moduli for both changing the polymer stiffness and changing the polymer content. And the typical results are, as I said, about twice as stiff, but they show the same scaling, including some of the nonlinear scaling, up to the point where the polymer content undergoes this pendular to funicular transition, where, as I said earlier, we believe the physics to change. In the numerics, however, we can also play around with things that we can't do experimentally. So in Utah's paper, we do quite a lot with changing the packing fraction or volume fraction. Again, the motivation behind this was originally, something like snow as well as sandstone. And snow represents something which fails in a very different way. It fails by a compressive failure, like a compression band, in the direction that they are compressing rather than a shear band. And one of the more intriguing things we find is with the same material parameters, the same physics, we can cleanly go between between 3 different failure modes of a compressional failure, plastic failure at intermediate volume fractions, and a brittle or failure by shear banding at high volume fractions. And if you look at the stress strain curves of those, you can see the very different modes of failure. At the high volume fractions, like the experiments, we have a brittle failure. If you look at the activity in gray, you find low activity until just before the failure point. You have a critical burst of activity when it fails, and the stress goes down rapidly past that point. At slightly lower volume fractions, we have sort of a continuous creep, and it smushes with a continuous activity to very high strains after the maximum stress is reached. At the very low volume fractions, there is bursts of activity associated with intermittent stress drops. And if you look at where that is occurring, you can find that these represent bands of activity happening normal to the direction of compression. Again, one of the more intriguing things, at least from my perspective from this, is that you can then measure things like how the modulus and the ultimate compressive strength depend with the number of contacts or with the density of contacts. And I won't talk much about this due to the sort of shortness of time, but this relates to some work that is undergoing recently about how stress chains affect the scaling of the material properties of things like sandstone or sticky spheres. Baxter's sticky spheres is one of the models used for this. And these predict very high power law dependencies of properties like the elastic modulus or the ultimate compressive strength on the density of contacts, which is consistent with what we're finding in the numerics. Yeah, this is just another mention of the sort of the compaction band. So if you look at where the activity is localized, the activity is represented by color here, and we go from a transition at high volume fraction from a shear band to a low volume fraction, a compression band, and this relates to some work, for example, from a group in Erlangen on snow, which was published a few years ago in Nature Physics. It's similar also to work Pedro Rice did on the compressive failure of foams, which fail in a similar way. So to summarize, what we've done is we've made a material property which consists of glass beads held together by polymer bridges. The physics of this is that we have bridges which are soft compared to the particles. And by adjusting the amount of polymer and the stiffness of that, we can change the stiffness and failure conditions of these materials over a wide range. They tend to fail at fairly high strains, order 0.1, and that we can show how the properties relate to the properties of individual bonds between particles. From the measurements that we've made of that, we've informed a numerical simulation which can reasonably accurately, it's slightly stiffer, but we think we know the reasons for that, can predict the way in which these materials deform and fail fairly accurately, and also allows us to explore other things which are not accessed experimentally, including, for example, differences in volume fraction. The experimental work was started 4 or 5 years ago. The first papers and scientific reports there that covers the experimental stress strain curves and the X-ray tomogram experiments. Second paper is about the way things fail. Yuta Yamaguchi's paper is mostly about the numerical modeling. And the one that is in preparation is all about the micromechanical testing, so actually measuring the strain constants. Thank you very much. And I think I have a few minutes for questions if there are. I think, Jordi, you're moderating. I'm going to break out of this because, as I said, I'm.
Yeah, well, yeah. We have opened the chat for questions, so
I'll put you back on.
Free to. Can you hear me?
Yep, but I'm not sure where the thing went to, but whatever.
Lucas, and
yep.
yeah, ask questions to Lucas. So I was curious about this activity. So you measured the activity as a broken bonds, right?
Yep.
Have you tried to compare with some measures on the displacements of the beds or something like that?
On the displacements, no. So, I mean, activity in an experimental perspective would relate to something like the energy released in acoustic activity. We're using it a little bit more glibly, simply to refer to the number of broken bonds in any time period. So yeah, when I say activity, it's a proxy for, and it's actually correctly done on the axis number of broken bonds in a strain window or time window.
Okay, and the bonds are reestablished once the.
No, they're not. This is the difference between what we're doing and something which is sticky or adhesive. So once a bond is broken, it fails forever. So we have a separation of time scales in our assumption from forming a bond and breaking them. So if you think about an avalanche, once things start to break, the avalanche goes in a few minutes, and once it settles down, it might freeze up overnight, so to speak. But the regaining of the strength of the material is slow compared to the way the damage accumulates. That's our basic assumption.
So simulating more than a cementation process, right? At the end of the day.
Yeah, we're simulating. My background's in failure, so these are simulating the way it fails rather than the way it cements in the first place. You can imagine a steady state where you reestablish the bonds, and that might relate to something which is sticky, basically, is the way it's sometimes put in the literature.
So now, if there is no other question for Lucas.
Okay, so I think if I press that, there we are. Okay, now I got the chat back.
Okay.
Okay.
Thanks again, Lucas. Then maybe if there is some more questions, we can open it after the last talk. Okay.
Thank you very much.
So the last talk of today, or this session, will be by Adriano Walandi. This is Adriano. Can you? So Adriano is from the Istituto Nazionale di Geofisica e Vulcanologia in Rome, Italy.
Hello.
Hello.
Let's see. Okay, do you see the screen?
Yeah, we see it perfectly. Whenever you want.
Okay, hello everybody. Thank you, Jordi, for this invitation and for organizing this workshop and giving me the chance to present a bit of my work in collaboration with other colleagues from Caltech or from France in Paris. Here, the original abstract I have written, I was talking about also some presentation about the El Mayor Cucapar earthquake. Here I'm going to talk just briefly about that, but mainly about the slow slip event in Cascadia. And as you will see, we have seen a lot of nice talks about lab experiments and lab results. Some of them also, some of the talks also about seismic data. Here I will bring you some geodetic data instead, just to see another aspect of how we can monitor the tectonic deformation. So the goal of this presentation wants to be to describe how to go from a system like or a description or an observation like the one we have on the left, that basically is a collection of GPS stations, and each of them is recording some displacement at the surface, to interpret basically characteristics of the underlying attractor of the dynamics. Here I'm showing the slip potency and slip potency rate. And some of the characteristics of this attractor, that will be the instantaneous dimension D and the extremal index theta. One driving question that I have in this presentation is, are the earthquakes a result of deterministic or a stochastic process? We have seen earlier today a presentation by Marisol Monterrubio Velasco that was talking about a similar topic about this, and she was saying that we do not really have access to all the quantities that we would like to have for a deterministic description, and that is true. For example, we don't have the stress on the fault, but even if we don't have all of them, maybe with having just one of them, and this is from the embedding theorem, you can still say something. If you have the full history of one of the variables of interest, you can still say something about the state of the system. So to describe what are the data at our disposal or that we want to use for this study, I'm showing here on the left, I was saying we use 352 GPS stations that total to a bit more than 1,000 time series, because for each of them we have the east, north, and vertical directions. And they may look something like what you see here on the right. There are 3 reference stations. There is ELISE, ALBH, and P159 that are indicated by some red diamonds here on the left figure. And you can see that there is a clear long-term, basically linear trend. Sorry. That is due to the subduction of the Juan de Fuca plate, that is subducting at a rate that is variable at about 25 millimeters per year in the south to about 40, 45 millimeters per year in the north. Then here we show also there is seismic activity at the junctions points. Like here, there are these stars that indicate the magnitudes larger than 5.5, and also here in the northern part. And these earthquakes can affect your displacement recorded at the surface, like with these kind of jumps. So what we do is we want to detrend and remove the jumps from this time series, and this is what we are left with, where you clearly see there are also post-seismic activity on top of what could be seasonal deformation and the eventual slow slip events. I will talk about slow slip events. The reason why is because for regular earthquakes, to observe multiple cycles of one segment that is failing, you may have to wait for decade time or even centuries. And we do not have a long history for that. Instead, for slow events, they have a small stress drop and you have repeated ruptures, as we will see. So once we have this kind of time series, we want to reconstruct what is the slip on the fault. And to do that, one option could be to perform an inversion day by day. We're studying a bit more than 10 years of data with data sampled daily. So you could do an inversion day by day and get the fault slip history. But this is computationally quite intense and you have to do a lot of inversions. So one solution that has been proposed was the one by Koziski-Abouak. The idea is to take your time series X. You have a bunch of them. We said a bit more than 1,000. We organize them in a row. So every row is a time series. And you can do a linear decomposition. What they did, it was with a principal component analysis or a singular value decomposition, that is this notation, where you have in the U matrix, basically you will have all the spatial contents of your components, and the V matrix will contain all the temporal information of your components. Then once you have these components, you can do an inversion of only the spatial parts, and you recombine with the temporal part to get the slip history. The problem with that could be that you have multiple processes that are affecting your time series at the surface. So what we did in the 2016 paper, it was to add or modify this PCA approach, introducing an independent component analysis. In particular, we used one based on a variational Bayesian approach developed in robotics and neuroscience. There was a group in Oxford. By Chaudhry and Roberts. And what we do once we do the decomposition, you can see that, for example, in this case, we start from time series like the one on the left, and some of the components are indicated here in the right. The V matrix, I was saying, each column is basically a component that is showing the temporal evolution of that component, and the U matrix will be the spatial response of that component. So, for example, in this first one in the top right, you can see clearly that there is a post-seismic activation. These are large earthquakes in the northern segment. There is clear post-seismic activation after 2011, and it is isolated to reference to the northwest stations, like indicated in the map. We have also other components that may look more seasonal. Like the second one, it is quite uniform in space. And the red line here is showing the temporal evolution of data recorded from GRACE, that is a gravity experiment. Also, this is a satellite experiment where you record the gravity variations with time in a given region, or it is a global experiment, so you see it all over the Earth, but we can focus on this region. And from these gravity variations, they are typically attributed to variations in the water content or the mass of water present. It could be snow, ice, or liquid water. And from this equivalent water thickness that you can calculate calculate what should be the variation, the response of the elastic crust. And this is having a very good match, so we can attribute this to hydrological loading. Then you may have components like the third one, where you clearly see a sawtooth pattern, that is the recurrence of our slow slip events that are focused in a certain region in this case. And the last component is basically one of those that could be attributed to common mode error that is typical in GPS studies. You will see something that is affecting the whole network and could be related to a reference frame error. Just a quick note on the Elmayer-Kukapa that I was saying, I will just mention briefly. It is also possible to separate contributions from different tectonic sources. So this was a study after the Elmayer-Kukapa 7.2 earthquake. And during the post-seismic stage, we could isolate a long-term decay, that is the one on the left, that we associated with viscoelastic relaxation, and a short-term decay that is instead well matched by rate strengthening fitting. This was a work with Jen Liu at JPL and Chris Rollins. In particular, for this one, what could be interesting, and it was the reason why then I got in touch with Jordi, it was the fact that for the after slip, so the one on the right, we know that there is typically a good matching with the clustered aftershocks that here are represented. The cumulative number of the clustered aftershocks is the pink line. And we have a good match with the geodetic observation of afterslip. But here we also have a good match between the viscoelastic deformation recorded at the surface with what are the background events that are not stationary in the post-seismic part. So it could be that there might be an influence at long range and long distance due to the viscoelastic component. But to go back to our slow slip events, I was saying once we have isolated the components that we attribute to the tectonic deformation related to the slow events, we can perform an inversion of the spatial parts of them, this U. And once we have these slip linear components, we can recombine them with the temporal functions and obtain the fault slip history. Basically, this fault slip history can be summarized in this video. We have a couple of points that are these two triangles that are basically representative of the time series at the top and bottom panels. What we show is the slip deficit. So whenever you have an upgoing curve, you are loading the system, and you arrive to a point where you have a failure, and here it will be then at this point in the northern part, you see that it becomes all blue, the color. Here we have the slip deficit rate. So when we have blue colors, we have a slip event, and we have yellow colors, you have a loading. And as you can see, on top of that, we're plotting all these black dots that are appearing and disappearing. They are the tremors recorded from independent catalogs. And they match very nicely with the inversion of the geodetic data. And you can see that we have events that propagate not only from south to north, sometimes they propagate from north to south, sometimes they are bilateral, and they all look like pulse-like ruptures. This plot instead on the right part of the video is just to show the relation between the coupling map that we have deduced from the long-term loading and the location of all the tremors. That you see there is a clear buffering between the two. So it is hard to say if there is a strong interaction in this particular subduction region between the slow events and the locked region where you may nucleate an earthquake. So it might be different from other regions. This could be a very interesting point of discussion and to investigate more. Like in other regions in Mexico, for example, we know that there is they are much closer, the two, and there is an influence between the two. Another way to look at the video is the image on the right that I maybe like even more because it's a static way and you can appreciate all the details better probably. The map here is just showing basically the cumulative slip, and we know that the northern segments are showing more slip in general compared to the central or southern part. And you can see here in the x-axis we have time, and in the y we have the latitude. We have attempted this segmentation. It can be also changed with time. The idea behind the segmentation, the rationale behind it is we locate all the regions that slipped with a slip rate larger than a certain threshold. That for us was basically the long-term loading, this 40 millimeters per year. And whenever that happens, we search for what are the regions that at least once during the whole time history slipped independently from the neighbors. So if you look at the segments 1 and 2, for example, that are the most active, it seems that they're almost always very highly coupled, like they are sleeping together here, 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 and so on. But at least once in this case, and in this case, one of the two slept independently from the other. So we decided to attempt this segmentation and move on. It will also be possible to change it. It is anyway clear that the northernmost segments seems to be to have a different recurrence time compared to the central segments, like those from 3 to about 6. And then the southern part is much noisier, and we will see also that indeed we will not be able to discriminate proper dynamics there. The green line is just to separate the old catalog and new catalog for the tremors. Having said that, now what we have is these 13 segments, and for each of them, we have the sleep history on all the patches for which we have performed the inversion. And what we can do is to calculate, for example, the sleep potency, that is nothing more than the integral over the area of the sleep, the integral of the sleep over the area where you are measuring it. And that would be basically all the pink dots. Then we have applied a low pass filter that will be this black curve. It is a causal filter. So we're not using a double direction. There is not information from the past, from the future. There is only information from the past. And you already can see that the segments in the north may have a bit more structure and dynamics than the one in the south that seems to be a bit more similar to noise. So now the question that we have is, given this observation, this observable, can we characterize the dynamics of the sleep events and some characteristical properties of the dynamical system? And I was mentioning before the embedding theorem that it says that if you have at least one variable, then you can calculate quantities like the dimension of the attractor, if there is an attractor underlying the dynamics. So I will not discuss about the embedding theorem because I don't have the time, but we are going to use the extreme value theory approach for the analysis of this dynamical system. This is basically some result from Faranda and colleagues that they applied it to atmospherical data, and we have adopted it for the study of slower earthquakes instead. The idea is, let's say that we have a point on the strange attractor, and it could be, in our case, we know that one observable of interest is the sleep potency rates for a given segment I. And so we have this observation and we assume that this is one point characteristic on the strange attractor at a given time t. Then what we want to calculate is to get what is the density is the dimension d is basically the density of points around this region on the attractor. And you can see here on the left a representation that they did for the Lorentz attractor. That is probably an attractor that everybody in the room is familiar with. And you can find what are the regions in the phase space of the attractor that have a higher or lower density. What we want then is to calculate this probability, and to do that we use we have to have an idea of what are all the possible states of the system, and we use all the sets of values that we have measured for the sleep potency rate, and we can build a variable like this capital Z that is basically looking at what is the distance between all the possible states and the given state at a given time. Once you have this variable, taking the negative log means that just large values of Z corresponds to small values of this distance. And you want to see how many events or how many times you're getting close to the region of interest. So what this transformation is helpful for is that now you can say that the extreme events of this Z variable, they will follow a generalized Pareto distribution, and you can calculate what is the scale parameter of this generalized Pareto that is telling you how spread they are, your values. And depending on how spread they are, you can calculate this density that is just related to the inverse of the scale parameter. So there are few quantities of interest of this, or few qualities that could be of interest of this D. And in particular, I'm showing here a plot that is similar to the one of the previous slide for the Lorentz attractor, but here we have a section of our attractor, if you want to see it that way. To read this plot, you have on the x-axis the slip potency, and on the y the slip potency rate. So whenever you have an event, you have that you are loading the system, you arrive to a point where you start increasing the slip potency and the slip potency rate. So we are going up, you reach a maximum of the slip potency rate, and then you start reducing your slip rate, and so the slip potency rate as well. You arrive to a maximum of slip potency that you have released, and then you start loading again the system until the next event. On the bottom part, there is a histogram of the number of times that you record a certain value of your dimension D. And this is of interest because it is possible to calculate the average dimension of the attractor simply measuring the average of this dimension D. And we found a value of the order of 3.3. Now, is this significative? Because every time you have a finite time series, there is always the chance to have a stochastic system that can describe it. If you have, for example, autocorrelated noise, you can always reproduce that particular observation. So one way to test if it is significantly different from a random realization is to perform surrogate data test. What we have done is we made the hypothesis for which all the structure in the time series is given by the Fourier power spectrum. Then you can go in the Fourier domain and randomize the phases. And then you go back in the time domain and you can recalculate the quantity of interest that for us is the instantaneous dimension or the average dimension. And once you calculate that, if the dimension or the statistics that you are interested in is different from the one that you have from the data, then you can claim that for that specific statistics, there is a certain significance of an underlying structure that is not generated by a linear stochastic process. So for the segments 1 and 2, that were the one in the north, we see that we have a significantly lower dimension that is consistent with the idea that if you have noise, you should have an increase in the dimension of the system. While for the other segments, for the segments 3, 4, and 5, it depends on the kind of filter that you apply to deduce the slip potency rate. They can be or cannot be significant, so this could be questionable, while for this one is always happening that we have lower dimensions. And for the segments in the south, it is not possible to discriminate the underlying dynamics from a stochastic system. Now, how to interpret these results? Because what this is telling us is not what are the equations governing the system. It's just telling us that we have a dimension of 3.3, so we have 4 degrees of freedom to describe the dynamic of all the segment, the dynamic of the segment number 1 in that case, so the segment at the north, or the segment number 2, or all the others. Then the question is, already this is surprising, let's say, because we have a system with a lot of potential degrees of freedom. There are a lot of particles in the Earth. And it seems like a collective behavior is emerging that you can describe it with a low dimensionality, in this case is 4. And the first thing to think of or to think about is something like a spring-slider model to describe friction. And to describe that, you have basically the equation of motion. That would be a second-order differential equation that basically is captured by the first 2 equations, plus a state variable equation. That would be the third one to allow for healing. But then to properly describe friction experiments in the lab, it has been proposed also to have a second state variable. And a nice study that was by Becker in 1999 was to study the case where you have 2 state variable, but an inertia-free system. And this could be similar, for example, to a slow event, having it inertia-free, because you do not have the dynamic part that or at least we think that it should not play an important role in the slow events. So this is reducing the system to 3 equations, so a dimension that should be between 2 and 3, and what he calculated was indeed between 2 and 3. Then to explain slow sleep events, it has been proposed, for example, by Siegel and Rice, the potential role of fluids in activating the slow events. And they added basically two equations about the pore pressure and the porosity. And this would basically bring us to 4 equations that is consistent with what we have found. Just a quick note about similarities with also regular earthquakes. It has been proposed, we have seen a lot of times in these 2 days talking about scaling laws, and it has been proposed that the scaling laws relating the duration of an event and the magnitude or the moment of an event is for slow events different from the one for regular earthquakes. The regular earthquakes is indicated by the green line here, and this one was the one proposed by Ide et al. In 2007. And what we find for the catalog in Cascadia instead is that, well, slow sleep events are actually following the same scaling law as regular earthquakes. Not only the one of duration and moment, but also area and moment, and they also have a Gutenberg-Richter kind of distribution. And this one on the bottom was an experiment instead done on numerical simulations by Dalviglio and colleagues, where they introduced also in the simulations pore pressure and porosity, and they could replicate basically the results that we have from Cascadia. So having done this connection, I will just comment once more on this dimension. There is one thing that is quite interesting, that is whenever we get to a region that is basically approaching the instability or getting at the end of the instability. So we are in the transition phase. We are in a metastable state between almost stable to full instability. We have a high value of the dimension of the system. And this could be potentially due to the role of the neighbors in affecting the dynamics of your segment. So we have basically an along strike segmentation in Cascadia. It could be that the neighbors start playing a role in controlling the dynamics of your block or your segment, and you will have an increase in the number of degrees of freedom seen instantaneously in that moment. The other quantity that is of interest that I didn't talk before is this extremal index instead that you can derive. And instead of thinking of the density of neighbors in a certain region of the phase space, we can think about for how long we stay close to a certain region of the phase space, and this will be the persistence time. So you can think of it as if you are in a fixed point of the system, you will have an infinite persistence time because you always stay there. And if instead you have a random system, you can be in that place in the phase space at time t, but at the next instant in time, you can occupy any other position. So you will have a very small persistence. So what you do, you calculate the inverse of this quantity and you normalize it between 0 and 1. And this is the extremal index. And nicely, in a recent work by Farhand and Vaienti has been proposed this connection between this extremal index and the metric entropy of the system. The metric entropy is nothing more than the sum of all the positive Lyapunov exponents. So to have a connection between the two, we can see that intuitively it makes sense, this connection, if we think, we said theta is the extremal index could be equal to 0 if you have a fixed point, in the sense that you have infinite persistence time, so the inverse will be equal to 0. And to have 0 for theta, you have to have a value of h that is equal to 0. So you will have no positive Lyapunov exponents, and so you are on a stable point. If instead you have a theta that is equal to 1, you have to have an entropy that is extremely large. And so you will have basically a random process. Having said that, we can then calculate what would be basically a predictability horizon as the inverse of this metric entropy that is telling you how quickly the trajectories in the phase space are diverging. And for this segment that I'm showing here, it was about between 3.5 and 65 days. These are extreme values from the minimum and maximum that you can get. We constrain a bit more. These are the values, again, from the extreme value theory. We used also nonlinear forecasting analysis to make these kind of predictions and see how rapidly the misfit in the prediction is getting using the neighbors in the phase space. And I don't have the time to get into the detail of the nonlinear forecasting analysis that is based on the embedding theory, but we find anyway something that is in the range of what found from extreme value theory. So this is consistent with that. Is of the order of 1 or 2 weeks. That is in general a fraction of the duration of the instability, because for slow events, we can have events that last from weeks to also a month. So to conclude and try to summarize all these points, a good thing is that we can extract information, the tectonic parts of the information from the geodetic time series that contain in continuous, basically, the information on the slip on the fault, and not only having a point process. Then we can infer something about the dynamic of the system, and we found that it is consistent with the deterministic chaotic dynamics for the slow events in Cascadia, with an average dimension of the attractor of the order between 3 and 4. That is consistent with a rate and state spring glider with fluid infiltration. Then the predictability horizon is of the order of a fraction or of the order of the duration of the instability event. So long-term prediction in a deterministic sense seemed to be not possible, and a statistical point approach seems to be the most reasonable and the best one we can have. For if we follow the analogy with regular earthquakes, and if we think of the instability time scale of the earthquake, that is just a few seconds. Also, this means that a long-term prediction seems to be not feasible, and so this could help only to have a few seconds of predictability for these kind of events. And it would be nice to test these kind of techniques also for laboratory earthquakes and numerical simulations. This is something that I'm working on, but we have seen plenty of lab quakes in these days. So I think that could be an additional metric of interest to monitor in these kind of studies. Thank you.
Thank you very much, Adriano. That was really interesting. If you have some questions in the audience, please indicate it in the chat. So I think Cameron has some questions from some details. Beginning, Cameron?
Yes, nice talk. You might have addressed this, but I missed like a couple of your first slides. I mean, is there any correlations between like the temporal change that you observe in the slip rate and the seismic like activity in the region?
So let me wait a second that it doesn't go back. So I don't know which slide you want to see.
We're just showing.
Can you, sorry, repeat which slide?
The one you're showing now.
Yeah.
10, slide 10. So I mean, how does this compare with the seismic activity in the region? Like this?
So for the slow events, I'm plotting here on the right, there are only the tremors with the black dots, not the seismic activity, so the large earthquakes. For the large earthquakes, we have that whenever there is one, there was something like this in the time series. There was a jump and a post-seismic decay, but that was mainly affecting the regions that are in the southernmost corner and the northwest corner. So where we have the most of the slow slip events that are in this belt of slow slipping region, there was at least looking at them, if there was activity, we have inverted for it also as a slip on the fault. But it could be that there is an interaction between the seismic part and the slow slipping parts, as I was mentioning when referring to this figure here. But we, in the analysis I've done, basically we have neglected that, saying here we have basically a buffering zone that is not, the earthquakes are not affecting the system. It could be, though, that there is an influence, and this could be also a reason why we see an instantaneous dimension that sometimes go higher than the value of 12. That was more or less 12. For the segments from 1 to 5, we saw instantaneous dimension going from 11 to 18 as a maximum. So if you are adding dimensions, that could be either that there is more noise or that there are farther degrees of freedom that are needed to explain the dynamics of your system. And that could be a potential interaction from something that we're not considering. Does this answer the question?
Yes.
So I had another question. So you mentioned that, I mean, from the latent state from the iterate, you get that you should expect dimensionality between 3 and 4. This is without considering any kind of interactions between the blocks, right?
Yes, exactly. Then if you want to add interactions, and if you think only for elastic interactions, basically what you have is the Borishnopov system, where you have the chain of blocks. And when I said a chain, and it is basically a segmentation along strike, is because if we look at the video, let's see if it starts the video. If you look at the video, it seems very much like there is a propagation of the events along strike here on this belt. And so the segmentation that we are making is basically considering each of these segments as one spring slider. And then you'll have the connection with the neighbor and the neighbor, but the neighbors are only along the strike and not along the dip direction. So once you have this chain, every single segment every single block is bringing 4 degrees of freedom to the system. And so if you add the neighbors, you will have 8 more, and you get to about 12.
Okay, thank you. There is another question by Ian. If you want to ask yourself.
It's not really a question, but it's, well, first of all, thanks. It was a really interesting talk. Some nice animations illustrating the variety of behavior that you can get on this one sort of plate boundary, you know. But I was interested in your formalization of the issue of predictability with the Lyapunov exponents. I'm not sure I've seen that before, but that is a really good insight into why these slow slip events might be more predictable than natural sort of dynamic earthquakes, you know. And it would be nice if you could map out that phase space, you know, by looking at slow slip events with different durations or something like that, to see if you could collect a database of them and see how the scaling goes as you get to more rapid propagation of these events, you know, where inertia becomes more important.
Yes, yeah, I totally agree with that, and this is why basically in the last slide, and when I say some of the current and future work, the idea is to try to compare with different subduction regions, because we know that there are differences. I mentioned that in Mexico, for example, we know that there is this flat part of the slab where you have the slow slip events that are basically intruding almost in the active tectonic part, the one that is coupled, where you have magnitude 7 plus. And we know that there is an interaction between the two. Here in Cascadia, instead, it seems that there is some detachment. So already that would be interesting to see if that can play a role. And then I'm looking at lab experiments with the results of the group of Penn State and INGV in Rome.
All right.
La Sapienza. So now that Chris Marrone is in Rome, we had the chance to interact with him and also with Cristiano Collettini and Marco Scuderi.
Yeah.
And basically, I started looking at some experiments where you have only basically quasi-static or a single event, almost periodic, and some others where instead you can have both fast and slow events. And I hope to have some interesting results soon on that, but I cannot really comment at the moment because I don't have something that I can really feel comfortable to say, oh yeah, it is like that.
No, I think it's a great idea to do that, you know, because you've got the control on the system, you know, by adjusting the friction in the experiment. I mean, the other thing is, that, people have looked for precursors to natural earth, to dynamic earthquakes. And quite often there's evidence of absence in the geodetic data. For example, in the L'Aquila earthquake, I think it's Amoruso and Crescentini had a study where they looked for precursors. And all they saw was essentially a co-seismic and a post-seismic effect. And that's actually quite common for these large dynamic earthquakes, So it's not just that we haven't looked. I mean, we don't know if they are there, but we have looked, and we've not found anything directly in the strain.
Yeah, the L'Aquila earthquake is very emblematic also because there is next to it there is the station of the Gran Sasso, is the National Institute of Nuclear Physics, and it is underground, is where they have basically from there they were receiving the neutrinos sent from the CERN, and so there is instrumented region underground, and there is a strain meter there. That is very close to the L'Aquila, but didn't record anything.
Yes.
Or at least I've not seen anything. I remember talking with Professor Albarello in University of Siena was saying that they couldn't see anything there.
Yeah, I hadn't heard of that. I'd heard more of the geodetic data from space, looking at the satellites and not finding anything.
Yeah, one thing could be interesting is also, and that is related to the last point here, like improve the filtering to attempt a real time. Because for slow events, I find that basically this predictable horizon is of the order of days. So potentially could be done with geodetic data. There is a problem that you have to wait for the final precise ephemerides from the GPS that can take up to 2 weeks sometimes, or even more. And I'm applying a low-pass filter that if you want to use a causal filter, you introduce delay in your signal. So I need to do something to solve that problem. But if it is true what I'm saying, that of course the analogy with the fast earthquake is still questionable, but it is out there. If it is true, that analogy for fast earthquake, we should go to the high rate GPS to see something, but the high rate is even noisier.
Yeah. Yeah, all of these time series can be difficult to analyze, but I mean, I really enjoyed the way you formalized it with the Lyapunov exponents and so on, and so it just introduces a degree of realism and quantifying predictability, because people like to think of it often as a binary thing. It's either predictable or it's not. And you get debates, and I was involved in this, 20 years ago or something. But I think it's really important to publish results where you've looked for something and you haven't found it, like these geodetic results, because that is a constraint on your model, and it's often a very strong constraint. And you've shown a nice kind of potential for maybe grading from a more predictable to a less predictable system when you do these regional studies and constraining it more in the lab. Sounds like a lot of work for the next few years, though.
Yeah, there will be stuff to do.
but yeah, thank you.
Thank you.
Okay, so thank you. We had some other question left for Lucas. I don't know, Cameron also was asking something to Lucas.
Yes.
Yeah, I'm still around. Yeah.
Hi, Lucas.
Oh, yeah.
Nice talk, by the way. So there was a slide where you showed like different failure modes toward the end of your talk. So do you think like if you look at the statistics of burst, I mean, will that fundamentally change with respect to these different failure modes?
Let me just skip it up. So we suspect yes, and that's one reason. Yeah, that's one reason why we plotted them in this way. But the statistics, the sample size was actually tuned to that of the experiment, which was built around the X-ray tomogram size. So the sample size is only about 3,000 to 5,000 particles. So we suspect yes, and we can see that sort of in the statistics here. There are spikes here for the versus a more continuous. So that we would describe this as more intermittent in the sort of mathematical sense, but we don't have actual formal proof for that because the sample statistics size are just too small. And we couldn't upscale the numerics to cope with the hundreds of thousands of particles we would need to make that more rigorous. There is some work by Ferenc Kuhn's group on some similar materials. I don't think he looks at the density, but at least in the brittle case, I think the result is before and after brittle failure, looking at the statistics of that and show that they are different. Yeah, we would love to have done that, but sample sizes were just too small to make it statistically significant. We suspect it's there, but yeah.
And a relevant question. So about the fracture experiment that you did, like that like mode 1 like fracture. So I assume that like the concentration of this like polymer like glue should impact on, again, like the failure mode. I mean, if you have like a low concentration, you should see like perhaps shearing bands, fractures. No?
In the geometry we used, it's pretty much it's a notch geometry. It's designed to test fracture propagation. So it's
if the material is soft, then you should see shear band, not really a fracture. Even if it's
I think in this geometry, yeah, you can get something going off at a weird kink angle.
Exactly.
We never really saw that. I think you are right that there are some materials that will do that, but we didn't really see that. We experimented with a variety of weight percents from about 0.5% to what was that, 3? These are all still rigid materials, so maybe down in the very low range where it starts behaving more of a sort of more like a normal granular material. But we didn't see that kind of mode.
So W is like, yeah.
It's the amount of liquid you add. So it's the amount of polymer. So 0.5% means 0.5% of the volume is made up of plastic. It doesn't sound like much, but it's enough to hold it together.
Have you played with the number ratio?
What do you mean number ratio?
Like the number of particles that are connected by these glues.
For the experiments, no. That's very hard to set. So that's the density of contacts. For the numerics, yes, we did, and that was effectively what we believe we were doing when we were changing the vacuum fraction. That's what we think is the effective variable. Is it changes the number of contacts. So Z in that lower axis there is the coordination number or the number of contacts, which affects things like the way force chains propagate, etc. So there's quite a lot of literature on that in similar contexts. But in the experiments, no.
Thank you.
Okay. How do I? Yeah.
Check if there is something else on. There are no more questions, I think, for this session. Tell me if I'm mistaken. So then what we can do is to leave this room open and for the next session that will start at 8 p.m. Central European time. So thanks again all the speakers of the session and of all the sessions beforehand, and see you in just 1 hour approximately. Tiran.
Thank you very much. Bye.
Bye.
Hi, Alvaro.
Hi, Mehdi. How are you?
Good, good. Thanks. And you?
Good. Have you tried to share the screen?
No, I'm going to do it right now if you don't mind.
Of course.
Why am I not seeing my presentation? Okay, there we
go. Okay, it works.
Let me see if I can make it full screen.
Yep.
So are you seeing it full screen? Let's just make sure that the videos are showing up. So the video is fine, right? Okay, perfect. That should be good enough. I will stop.
So you are in Canada, right?
Yes, I'm in Ottawa. So it's almost 2 p.m. here. I realize it's really late for you guys. So thanks for staying up.
Yeah, well, we have to organize these different sessions at different times so that the speakers could have more or less adequate time for them. Hi, Kamram, how are you?
Hi, Alvaro. Fine, how are you?
Good. Would you like to try your presentation, just in case we can?
Sure. Shall I share my screen?
Yes, please. We can see it.
Is it up now?
Yeah.
Okay, good.
Yeah, now it's full screen.
Shall I stop sharing or?
As you like, we can leave it there since you are the first speaker. Are you now in Calgary?
Yes, I am.
But you were before in Europe, right?
Yes, I was.
Or
yeah, I spent some time in Grenoble.
This is still a bit early. Since we will start at 5, we have these 10 minutes so that the people can start connecting and so on. Here we have Jordi also already. Mauro Cacache, Alexis. I will be back soon.
Hi, Alvaro.
Hey, how are you, Jordi? You made it on time.
I can see you. So
you can or you can't?
With CRM3 at the end?
Sorry?
Could you connect with CRM3?
I logged in as Alvaro, as before, with my account.
Okay, so I tried. Yeah.
How are you, Jordi?
Fine. I will try to connect with the other
it on time.
account.
Mhm.
I can see you. So
Can I help?
the CRM3 at the end.
CRM3. No, it's not here. There is one Jordi Baró, and you are Jordi Baró Urbea. Mhm.
I was gonna send a private message to Mehdi, but my screen is shared, so.
Ah,
Yeah, are we going to talk about the fracture stuff or granular stuff, Kamran?
It's a mixture.
Okay.
Why am I connected twice now? I don't understand.
which account did you use before?
I don't know. I thought it was CRM3, but it's weird. Yeah, so it says that it's recording the other one. Okay.
let's wait a couple of minutes more. Okay, so I think that we can start already, and maybe other people will join us after starting this presentation. So it's my pleasure to introduce the next talk by Kamran Karimi, currently at the University of Calgary in Canada. He has been before working in Grenoble in France. The title of this presentation is From Plastic Flow to Brittle Fracture, the Role of Microscopic Friction in Amorphous Solids. So thank you, Kamran, for attending to this workshop, and we are looking forward to your presentation.
Thanks, Alvaro, and a big thank you to the organizer for this opportunity. You can see the title of my talk, and this is a work that I did as a postdoc at ISTER in collaboration with Jérôme Boyce and David Amitrano. Let me give you our motivation, which is a granular experiment which was done in Rennes at Jérôme Crassu's lab. So a typical like biaxial test, and they had like a novel method of measuring microscopic strain within the granular sample based on the scattered light. And like the dark regions represent like active regions. And you can see that these precursors occur before the failure, and at larger strains, the deformation localizes into these two clear shear bands. So they also studied the correlation function, which is, I mean, if you sit at an active site and ask at what angle it's most likely to see the next event, the answer is, I mean, the answer can be given by this correlation function, and most likely at 53 degrees, you can see that the next active event might occur. So surprisingly, the angle corresponding to the shear band was different than the angle associated with these precursors. And so our motivation was to understand this and sort of develop some theoretical background to explain this difference in angles, and also reproduce their results by numerical simulations. So if we zoom in and within the sample, we can see that these precursors are quite structured in a space and are pretty long range, like compared to the grain size. with this characteristic angular symmetry, with this angle of maximum correlation. So how we can model this? This is the motivation of our work. So let me start with some background on the Eshelby theory. A seminal work by J.D. Eshelby in the late 50s. So the picture is that for an elastic medium with a soft inclusion within the matrix, under the load, the inclusion can go through this shear transformation. And since it is soft, you can imagine as, that, I mean, if it is too soft, it's as if there is hole like within the elastic medium. So the stress tends to concentrate near this soft inclusion. It tends to decay as you get further away from the inclusion. So Eshelby solved this problem and gave this closed form solution for the spatial decay as well as the angular distribution of the stress. So 1/r² indicates that the stress perturbation is quite long range in a space. This is like a two-dimensional problem. And the angle, the exponent depends on the dimension. And you can see that there's fourfold symmetry. So here I'm showing like the stress perturbation due to this shear transformation zone. So we based on this form, we get like positive lobes and negative lobes. And so maybe I can, so within this region, so there is a lot of pushing due to this shear rearrangement. And the shear in this slope tends to be negative. And also, there is a lot of pulling in this part, so this is why we get negative shear for those bluish lobes. And we can play the same game with the pressure. So this is how pressure decays in a space, and also its anisotropic form. So for pressure, we get this bipolar symmetry. So we get two lobes, positive and negative. And it is easier to visualize because, I mean, the pressure. So because there's a lot of pushing in this direction, so pressure is positive, and pulling in the perpendicular direction. So we get negative pressure. So why I'm looking at the pressure and shear? So because, well, I mean, due to this rearranging zone, we get like regions in a space that have positive shear stress. And if you look at the pressure as well, there are regions that sort of overlap with the positive shear sign, which have negative pressure. And since pressure in many frictional materials has this stabilizing effect, so we can expect that regions with positive shear and negative pressure are quite prone to instability. So this just comes from some classical failure criterion proposed by Moore and Coulomb. This is why we should be looking at what is commonly called as Coulomb stress, which is like a common quantity measured in the context of, in many geophysical contexts. For example, a main shock, like an earthquake occurs and it perturbs the Coulomb stress in the neighboring regions. And aftershocks tends to localize within regions with positive Coulomb stress. So there's a linear relationship between Coulomb stress and shear stress and pressure. So as shear increases, Coulomb stress increases, and as pressure decreases, Coulomb stress increases due to this stabilizing effect of the pressure. And there is some material parameter, which is like local friction, and it controls the sensitivity to the pressure. So here I use this friction angle, and this is like the perturbation in Coulomb stress that I get due to this rearranging zone. And as you can see, like the positive lobes are slightly tilted up due to the fact that in these regions, pressure tends to decrease, and you should be looking at the combination of the stress and pressure based on this Coulomb stress. And I mean, this is like the closed form solution that you can get by just maximizing Fy. And theta gives you the maximum Coulomb stress direction. In this case, it's 50. And perhaps you have guessed by now that this is rather close to the angle that was seen in the experiment. We may also look at like a dilational transformation zone, because like in frictional materials, like locally you might get dilation due to shear. So for this dilation, pressure field is trivial because it's isotropic. It increases pressure everywhere. So it won't have an effect on the angle of maximum Coulomb stress. But again, it can cause perturbation in shear. So again, there is a lot of pushing to this part. So the shear will have negative sign, and pulling pushing in this direction. Okay, so pushing in both directions, but here you get negative shear, and in this region you get positive shear. So if you combine these two, like the shear deformation and also dilation, you can get again some theoretical prediction for the maximum angle associated with the Coulomb stress. So again, this is due to friction, and also we have the ratio between dilation and shear. So if dilation is 0 compared to shear, then we're back to the case where is basically you can have 0 dilation, and then it would be easier to interpret this maximum angle direction. But in general, the dilation should be negligible compared to the shear. So, I mean, in an elastic solid, it's usually less, it doesn't tend to be quite compressible. So this term is usually smaller compared to this frictional term. So, and again, this angle could be determined by 2 ingredients, not 3 ingredients, sorry. The ratio between dilation and shear, and also local friction. And you have, I mean, everything is based on linear isotropic homogeneous elasticity. So that's a big assumption. And maybe you can, I mean, we can play with these 2 local or material based parameters and sort of give a better match with the experimental results. So the take-home message is that local friction and dilation are important in terms of the dynamics of these precursors that occur prior to the failure. So let's move on to the second part of my talk. So I also did particle-based simulations to reproduce the experimental data. So it's also known as discrete element model, or granular dynamics. There are different names, but essentially we have got a bunch of disks that can interact with each other through normal or tangential forces. So if you cause overlap between particles, you have to do work. So this is why the spring is there, and particles can slide on past each other if you overcome the friction between those. So given that, I also sort of link the system to a barostat in the x direction to mimic the biaxial test where the pressure, the confining pressure is controlled. And you can solve equations of motions and see how the system evolves in time and space. A quick look over some simulation details on protocol. So normal spring constant, linear springs, force is proportional to the overlap. Tangential force is modeled by a friction, like a friction or tangential spring. We have like Coulomb's friction law, so friction cannot exceed a prescribed fraction of the normal force, which is mu. And we have also some mean drag represented by F vis, and also some paired drag given by these time scales. So we can just integrate the equations of motion by, so F equals ma, right? So the sum of forces should balance the rate of momentum change. And also we have torques due to friction, which should balance the rate of angular momentum. So given those, we can just solve these equations and see how the system responds to the compression. I chose two friction coefficients, mu equals 0, so frictionless disk, let's say. So this is why you can see only normal stresses on these particles. And I chose the friction of 0.4. So particles can have normal forces as well as frictional forces. So here I have a small video. So under compression, so the formation is mostly homogeneous until you get this instability. So particles exchange contact, and here these polygons show that, I mean, the deformation is purely or very close to pure shear. So there is no dilation. I mean, if you can measure the area associated with these polygons, there should be really small change compared to the shear. So, and you can see like these clearly see these shear deform, or let's say shear transformation zones associated with these particles. This that was for a frictional disk, frictionless disks, and we can play the same game for the frictional case. And here you can see like two like large blocks sort of slide past each other, and you can see like significant dilation. So due to like the roughness of the surface due to polydispersity of the particles. So in this sense, we get like two really different elementary deformation mechanisms associated with the frictionless particles and frictional particles. So here it's like I'm showing these deformation, these transformation zones at the sample size level. So on the left, which is associated with the frictionless system, you can see that events are really scattered almost homogeneous all over the space, and they're quite short range. And on the right, for the frictional system, they're more like crack-like extended features that are quite localized in the space. And so this transition seems to be controlled by the local friction coefficient. We made an important observation in terms of this different elementary deformation mechanisms. In a frictionless system, we see more like a plastic flow type behavior, where particles only rearrange, exchange contact without going through dilation. So the dominant deformation is shear. And they're quite localized in the space, whereas in the frictional flow, we get fairly large blocks of particles that slide past each other, and which is accompanied by a large dilatancy due to like the roughness of the slip surface, let's say. So how does this impact, let's say, the bulk behavior? So let me tell you what I'm plotting here. On the left, I'm showing the macroscopic stress, or the bulk shear stress on the left, versus strain, the black curve, and the right here, the red curve is the volumetric strain. So and on the right, I'm showing like the local strain. So I have got this displacement field, which is accumulated over one of these drop durations. And in the background, the color map shows the strain. And you should see like a footprint of the HLB, sort of HLB-based picture by looking at the color map. So like increasing the shear along 45 degrees, and you get also negative lobes. And if you look back at the response, there is some initial quasi-elastic regime, which corresponds to initial compression, and then the system enters like a plastic flow regime with these bursts, which is also apparent in the volumetric strain, which fluctuates, but there is almost no net volume change. So the system flows like an incompressible solid, let's say. And similar data set for the frictional system, but we get quite different behavior. So quite long initial elastic regime, which coincides with like compaction, initial compaction, a peak in the stress or a stress overshoot, and then there is some weakening regime with these stress drops. And the minimum in the volumetric strain occurs before the peaking stress, so it might be a good precursor. And then after that, due to, as the movie showed, due to those, due to roughness, let's say, we are getting a lot of dilation. And if you look at the color map, so shear tends to be quite localized and quite extended, which kind of resembles like mode 2 shear crack in solids. To quantify those sort of contrasting deformation mechanisms, we used correlation functions of the strain, local strain field. So, the map shows that, again, we get this quadrupole symmetry. This is for the frictionless case, mu equals 0. with these positive lobes along 45 degrees. And here on the upper left, I'm showing the spatial decay along these 4 angles, along 45 and 90, and also the conjugate angles 135 and 0. And you can see that like 1 over r squared decay seems to be descriptive of the decay along all these 4 angles. And also here, for a given distance, I look at the anisotropy associated with the correlation, and you can see that this quadrupolar form is a good fit to the data. Again, similar data set for the frictional system. So like this quadrupolar form seems to be distorted due to friction, and we get like a bigger angle, almost 60 degrees. And if you look at the spatial decay associated with the correlation function, looks like we get like a shallower decay up to, at least for along these 2 angles, 60 and 120, along those shear bands. Rather shallow decay up to some characteristic lengths, and then maybe like a faster decay, which might be closer to the 1 over r squared decay for these 2 angles. And for 0 and 90, we get like a steeper decay, we get a shallower decay all the way. So I also did some stress-based test, like we only control the stress, much like a creep test, and we increase it at a constant rate and see how the signal, which is like the stress drop here, evolves with as a function of distance to the critical point, let's say. The one on the left corresponds to frictionless, and on the right, frictional system. So the linear, you can see like this linear trend in the avalanche size statistics. And the y-axis in log scale. So this should indicate an exponential type growth with distance to the critical point. Whereas for the frictional system, you can see this algebraic decay of the avalanche size, which it might indicate presence of the critical behavior. Whereas this feature is absent in the plastic flow case. So with that, I put up my conclusion slide. I think I already went over time. So I just put it up there and take questions. Thank you.
Thank you very much, Kamran, for this very, very interesting talk. We have a question by Mehdi Burakba. I don't know, maybe Mehdi, would you like to say it?
Sure. Sure. Thank you, Kamran. Very interesting talk. My question was, what do you think is the reason behind the difference in the orientation of the local slips that you showed and the global shear band that shows up at the end of the loading? So at the beginning of the talk, you mentioned that these angles are different, right?
You're talking about this in the experiment, right?
Yep.
So, well, it's really mysterious to us too. So, I mean, because like the molecular dynamics simulation showed like a smooth, so maybe I can show you how things evolve. So maybe I can play this movie. So this is basically the evolution of, or the dynamics of the precursor. So this is the correlation function, and I measured the angle corresponding to these features. So you can see like it's like a smooth evolution of the angle until it stabilizes post, let's say within the post-failure regime. So this is we found in the particle-based model, but in the experiment, it looks like it's like a discontinuous sort of type transition where the angle of precursors doesn't agree with the shear band angle. So there seems to be some discontinuous type of transition going on in this system. So
Thanks.
Cameron, how is this deformation seen in these experiments? Is also a photoelastic material with seen through polarizer?
No, they are not photoelastic. As a matter of fact, they are like opaque glassy beads, very tiny, maybe of the order of 100 micron size. And they have like a source that sheds like laser light on the sample and then gets scattered, and they have like a high-speed camera that sort of records the intensity of each frame. And by comparing, like by doing cross correlation between the intensity field taken at different frames, they get this correlation or deformation fields.
Mm-hmm. Thank you. There is also a question by Jordi Baró. Jordi, would you like to say it aloud?
Yeah, of course. Thanks, Cameron, for the talk. So I was wondering if so when you compare the frictionless with the frictional model, I was wondering if there is an equivalent of the frictional model when you consider Lennard-Jones potentials. I mean, when you are trying to model amorphous solids, it looks like everything will give place for through creep, right? Is that right? Or
I mean, if you're talking about bulk metallic glass, for example, I mean,
yes, for example, yeah,
there's not really friction. It's like it's more like a molecular glass, let's say. So you don't have friction and atomic scale, let's say, unless you fracture the sample, and you might get sort of stick slip type behavior between the fractured, like maybe micro-fractured surfaces. But apart from that, I don't think that this is directly comparable to those kind of systems. I mean, a real solid. So it might be comparable to like a cemented granular material where you have like cohesive interactions and on top of frictional systems, and where you might see some brittle fracture. And I mean, if you're able to tune maybe the friction between particles and cohesion, as Lucas showed in his experiment, I mean, you might be able to see this transition from sort of plastic frictionless flow to a frictional flow within, let's say, the context of a granular system.
Thank you.
Does that answer your question?
Sure. Yeah, thank you.
Ezequiel, oh, sorry. Nauman has another question. Would you like to say it aloud?
Sure. Thanks, Cameron. I was just wondering if you go back to the slide that you showed the equations on for the DEM, you seem to have drag. Could you get into some details about what that is doing in your model? The viscous drag that you...
There is like two types of viscous drag. First is what they call mean drag. So it applies like a viscous force on the particle based on its absolute velocity. And here is a time scale. So it's as if your particles are within a solvent. And I mean, so if you move them, you have to overcome the drag which comes from the solvent. And the other one is what they call pair drag. So maybe the symbols here are not helpful. So Vn here is the relative velocity. So it just comes from the interaction between particles. So you get energy dissipation due to collisions, and both in normal and tangential directions. So, and gamma n and gamma t control the rate of dissipation.
Okay. Okay, thank you. Yeah.
And we have a final question by Ezequiel Ferrero. Would you like to?
Hello. Yes, you listen me? Hi, Kamran. So you show this in the particle-based simulations that you detect some plastic rearrangements that they don't look like echelons at all. They are more like fracture lines or things like this. My question is if you expect in a much larger system to recover at larger scales the same, let's say, statistical physics that we observe for HLV-like models, HLV-like events. Do you think that it's just a matter of scale, or it's a completely different picture that we cannot catch with our classic elastoplastic models, let's say, for example?
I don't think it's a size effect because at least
no,
in the friction.
I'm not saying size effect. Yes, I know that you add friction and then you have these plastic events that are extended objects. They are different than a localized rearrangement. But is this always, let's say, percolating the system, or you can have
in the case of the frictional system, it always percolates the system. So this might be why you're saying this critical type dynamics. But here, I mean, they're quite short-lived, let's say, and they don't percolate to form shear bands at least in this model. So so at least for this case, I wouldn't expect to see any fundamental change if I increase the system size, because they're always local and doesn't seem to sort of talk to each other, and perhaps they wouldn't percolate if you increase the system size. But, as opposed to this case where, I mean, you can see these structured shear bands, and if you increase the system size, I mean, the scale also increase with that. So I'm not sure if I answered your question.
Oh, yes.
Hello?
I mean, you have answered. I'm not sure if I have the right question to ask. But yeah, I mean,
maybe a small amount of friction, because
yes.
Because I'm not sure, because you can play with friction, and I don't think there is like a characteristic friction value below which
Yeah,
you
what
see this.
I'm saying is that it's just adding friction. Maybe it makes a bigger plastic event, and then in your coarse grain elastoplastic model, you have just to choose a larger length scale for the element size. But my question is if it was just that, or there is a completely different physics that we cannot catch with a HLV-like, in generalize, if you want, let's say a propagator that has positive and negative kicks or signs according to an angle. It can be quadrupolar or something else. But for anything that has different signs, I would expect the same statistical physics to emerge.
So I made a comparison with the fracture, like mode 2 shear fracture. So, and I mean, maybe you can, you should implement the kernel that represents like the redistribution due to fracture, not an HLB inclusion, which is, it has a different form than HLB. For example, in 2D, HLB goes like 1/r squared, and it has this this nice quadrupolar symmetry, whereas in this case it's more fracture-like because it's kind of discontinuous. I mean, if you look at this anisotropic.
Yes, I see.
So, I mean, in terms of, in the context of elastoplastic model, I think like maybe an ad hoc, let's say, solution is to implement a kernel that is more compatible with descaling, and maybe like the one that you get from a mode 2 shear fracture
I see.
might be more convenient. I mean, it's something that you guys can try.
Sure.
And there is a very last question by Osvani. The experiments and the simulations are 2D or 3D? I understood 2D, right?
These are all 2D simulations. But in terms of theoretical predictions, I think like the decay becomes steeper. So it depends on the dimension, and also in terms of you get actually 2 angles because it becomes 3D. So the theoretical.
But
generalized, I mean, you can make it more general than this and run 3D simulations too.
that's actually my question, because in experiment, can you hear me?
Yes.
Yes.
Yeah, in the experiment, we know that it's a bulk, it's a 3D, and they have access only to a really thin layer. So the measurement is 2D, but the real experiment is 3D. So in the simulation, you could have access to 3D, so to the actual dynamics. So everything is 2D, or the 3D is playing something in there? That's my question.
The simulation is 2D, but even in the experiment, I mean, I don't think there's much going on into the plane. So, I mean, perhaps you get like a nice shear surface, I mean, shear plane. I mean, into
But
the depth.
you mean the physics of the experiment is it's just happening on, I mean, if we make cuts, because that's a problem they have. They can have only access to a really thin layer with our technique. Donc, I mean, with the simulation, the simulation say that this is just 2D. And it means that everything is happening symmetrically if we make cuts of the sample, or everything takes place at the surface, or whatever. Is 3D is important or not for the? Can you can explain everything with 2D simulations?
I mean, in
what
terms
that means?
of angles, I mean, we develop a theory which can, I mean, 2-dimensional theory that can describe or at least make a prediction on the angles. And I think it's not a bad assumption that this is really like a shear surface, and I mean, can be effectively treated as a 2D. Or, I mean, one could also do like a cylindrical experiment. I mean, then, and also the simulation. So to have like this sort of isotropic sort of confining pressure or axisymmetric simulation. So there is no, I mean, the shear band shouldn't favor any particular direction. So
okay,
I'm not sure if does it answer your question?
Yeah, it's okay. Thank you.
Well, thank you, Kamran. We will move to the next talk by Mehdi Furaka, who is connecting to this meeting from Ottawa, Canada, from the Carleton University.
Yes, okay.
Thank you for waiting, Mehdi. I prefer not to stop the discussion since this is a bit more, let's say, relaxed.
No worries at all. Okay. Let me make sure. Okay. Well, thank you, Alvaro, for introduction. Good afternoon, I think, to everyone. Let me start by thanking the organizers and Jordi in particular for putting together such a high quality and interesting workshop, and the queue of very interesting talks, and also thanks for including me. So I'm going to talk about failure in granular media, and I've been trying for a number of years to connect the notions that are used in engineering realm to the concepts in physics. And understandably, since my background is in engineering, I have very limited knowledge in physics, but I've been fortunate to be able to collaborate with Jörn Davidson at University of Calgary and Jordi since we spent some time together at University of Calgary. I would also like to acknowledge the contribution of my other collaborators, Richard Van, Niels Kreut, Francois Nico, and Felix Dahl. So as you can see, obviously my topic is a little bit too general and too pretentious, so let me narrow it down a little bit. I'm going to try and unify some of the concepts in engineering, concepts like critical state and plastic yielding that is often used in soil mechanics, with the concept of jamming transition in physics. And we'll see if I can succeed. So traditionally, soils are looked at or modeled as a mixture by mixing the theories that come from solid mechanics and fluid mechanics. So basically, the point of view is traditional point of view has been a continuum approach. We've seen in previous talk by Kamran how Moore Coulomb failure criteria is very potent in explaining the failure and deformational regimes in soils and in geomaterials. These concepts have been extended, more importantly, to give rise to what is known as critical state theory, which defines the yielding and failure at the same time. So the lines that we see over here, these are similar to Coulomb failure lines. But in short, the critical state theory, it defines an attractor. It defines attractor states that you can see in the bottom figure here in terms of volume or the porosity or the void ratio of the sample, and the mean stress, the hydrostatic part of the stress tensor. It starts by defining these attractor lines called critical state lines. These are states towards which the state of the material move during the deviatoric loading. So if we put the two figures together, so this is P and Q. Q is the deviatoric stress, P is hydrostatic stress. This is similar to the shear stress. This is hydrostatic stress, and basically what we get is a manifold in the space of P, Q, and V, V being the volume or the porosity, and that is our critical state. That's the attractor that the sample moves toward. And basically, we can now people now define new state variables by using the distance of the current state of the material to this attractor. This is the basics of critical state theory. It's built on ideas such as yielding and the general framework of elastoplasticity. However, during the past 50 years or so, people in engineering field started to look at soils as an assembly of discrete particles, and this quickly overlapped a lot with the physics community, as they have been for years studying such systems. So in this picture, instead of in continuum level, we talk about stress and strains, but when we go to the micro level, instead of a stress, we are dealing with a network of forces. We have seen yesterday in the photoelastic experiment in the talk by Ariel, who showed nice visualization of force distribution. And then we're talking And instead of talking about the strains, we are talking about the relative displacement of these discrete entities or particles. So we can see that clearly at this level, at the micro level, we are dealing with different variables. Some of them that I use in this talk is simple ones, coordination number, which is the average number of contacts per particle, which is closely related to a static redundancy or hyperstaticity of the sample. We have the average contact force, and fabric anisotropy, which is basically the anisotropy of the contact orientation, this vector, and it gives us a measure for anisotropy of the sample. We also have anisotropies for normal tangential forces, but I'm not using these in this talk. So now with these information, we can look at the sample and how the state of the sample evolves from a micromechanical point of view. So the results here are from DEM, and the previous talk by Kamran made my life much easier, so I don't have to explain the details. It's the same. You're looking at a 2D test. Biaxial, the lateral stresses are kept constant, and the vertical stresses are increased by applying a constant velocity. It's a strain control on the other direction. So we're looking at a typical dense and loose samples, and we see that for the loose, as we expected, the deviatric stress, as defined here, is a ratio. It increases for the loose, and it reaches a steady state. But for the initially dense sample, for which the initial porosity is much smaller, we have a very rapid increase. You can see it's almost instantaneous. It goes up, it reaches the peak, and then it goes back down beyond the peak to the same steady state. Now, when we move to micromechanical realm, we have a quite different story. So here we are looking at coordination number, it's number of contacts, versus fabric anisotropy, which is the anisotropy of the contact network. So we see that if you take point A and B for the dense sample, for the initially dense sample, in this range, we see that basically not much is happening, and only the deviatric stress is increasing. But if we look at the contact network, we see that a lot is happening from point A to B. The assembly is losing so many contacts. The coordination number is decreasing, going from A to B, and the anisotropy is increasing because the contacts are not lost the same along different direction. We see that the contact distribution changes. So we have a very rapid initial realignment of the contact network with basically negligible strain. And then after the peak is where we see large strains taking place, which is in this zone. So basically, this is explained by looking at different mechanisms that contribute to change in contact structure. So the first one is the elastic deformation. The particles can move toward each other as long as sliding is not happening. We call it the elastic deformation. It can change the structure, but not much. The particle can also slide and roll, which dissipates some energy and is not reversible. But what's interesting is this third kind of change in topology of contact, which is due to loss and gain of contacts. And we've shown that these things are not really reversible if you reverse the load without any dissipation. These things does not go back. And many of the strain behaviors that we see in granular material that we cannot explain using continuum mechanics are associated with this type of events. Okay, if you go back to this picture, and this is a picture that I'm going to refer to a lot in this talk. Now we see that if you look at the dense sample, we have initially this large range where essentially the contact structure, the contact network is evolving due to contact gain and loss. It's very rapid. No strain, you can barely see that purple zone in the left-hand side. And it gets to a limit where it starts showing the global deformation, and after it reaches the peak, it starts to show large deformations, which is due to contact rearrangement due to sliding. Okay. One thing which was interesting to me, and it was the start of this sort of reasoning, was that we can see that the structure starts to evolve when the state of material in the micromechanical space is aligned with the loose sample. You see, for the loose sample, the coordination number is increasing a little bit from this point to that point, and this is the critical state. This is a steady state at the end. It's called critical state in soil mechanics. So we see that the large deformation starts to take place when the state is more or less aligned with this line. So there seems to be something meaningful associated with that line. We start looking at that by looking at different initial states, and we see that almost for all of these states, the micromechanical state of the sample approaches the same line. It stays on the same line when it reaches it, and then it goes to the critical state at the end. And it seems that this line is a sort of threshold for coordination number that cannot be crossed in quasi-static simulations. Remember that coordination number is related to static redundancy. So static redundancy is being decreased. There seems to be a limit, a minimum limit for static redundancy, beyond which we appear to have no static equilibrium. And we already see some connotations with jamming transitions, because jamming transition is also related to has also been related to static redundancy. Okay, so we see the threshold, and the threshold, as we see here, is defined. If you go to the loosest possible sample, it gives us that line. It gives us a threshold. So next step, we simulated a bunch of different loose samples to get this limit. So we changed the confining pressure or the lateral pressure or hydrostatic pressure, and we get a sort of manifold in the space of coordination number and fabric anisotropy, and also rigidity ratio. This rigidity ratio is basically the relative displacement at contact points with respect to particle size, which is related to hydrostatic pressure divided by the stiffness of particles. So it's a comparison between applied stress and the stiffness of material, and we can see that we get a manifold by connecting all those loose simulations. Now, what we did next was to compare a bunch of different simulations with different loading controls, with different initial conditions. And the interesting thing was that all those samples, their micromechanical state would evolve toward this manifold, reach that, and they would all stay on it. It seems to be a very good micromechanical attractor, and we call it the stable evolution state, or SES for short. And I will say, I'll talk about why this name is chosen in a minute. So this seems to be a very good attractor. And keep in mind that the critical state is also on that. It's a point on this surface, and it seems to have some relation to jamming transition, but we are not clear about it yet. So this idea has been used actually in constitutive modeling. We developed purely constitutive model for granular material based on this idea of SES, and we use the distance, the Euclidean distance to this manifold as a state variable that gives us the proportion of different mechanisms that change the behavior of the material. For instance, here we are seeing the percentage of the external work that is being dissipated due to frictional mechanisms, and we see that at the beginning it's 0, and as we reach the SES, as the distance is decreased, it approaches 1. Okay, the relation to critical state can be shown a little bit more. The critical state, if you remember, it was a line which related the hydrostatic pressure to the porosity or void ratio of the volume. Now, if we take this this manifold and we project it on the horizontal plane, we get contours of constant fabric anisotropies. And if you remember, the rigidity ratio, as I mentioned, it's proportional to hydrostatic pressure, and coordination number. It has been shown, and we can show that when this state is reached, the coordination number has a 1-to-1 relation with void ratio or the porosity. So we can directly say that these lines of constant fabric anisotropy can be looked at as different critical state lines in the space of void ratio and P with different fabric anisotropies. So we see that the theory does not predict a unique critical state line, but it says that critical state line actually depends on fabric anisotropy. And interestingly enough, this is what people have been trying to do. People have been trying to implement the effect of fabric anisotropy into the critical state theory in soil mechanics. And here we just get this naturally and organically out of the theory. So we do see the how this idea of SES gives us a more generalized version of the critical state theory. Now here, this is the manifold, and the dense material is approaching this from the right-hand side. So we saw that at the very beginning, we do not see much of the structural rearrangement and dissipative deformations. It seems as though the sample is so overdetermined or jammed that it's statistically it can have equilibrium, but the structure cannot evolve. It has to lose the contacts and approach the isostatic limits so that the structure can evolve. So on the right-hand side, we have a static equilibrium, but a structural evolution, the global structural evolution, is not possible. On the left-hand side, if you manage to cross the threshold, it seems that the sample becomes unjammed. The structure can evolve, but there is no static equilibrium. It's only along the surface that you can have them both. You can have a static equilibrium and a structural evolution. And actually, we'll see later on that this is actually a going back and forth between the two regimes because of these sort of micro avalanches. So at this point, we had a good we established a good relation between this concept of SES and critical state theory, with yielding and critical state. But the relation between SES and jamming is still remain to be studied. And at this point, I was fortunate enough to be next door to complexity group at the University of Calgary. So with Jordi and Jörn, we started studying these fluctuations in stress and in energy to see if this state is really a phase transition state or not. Okay. So what we did was we did a quasi-static simulation. At the bottom, you see the deriving vertical strain. We start driving with a constant rate, and as soon as a threshold for the kinetic energy of the whole sample is reached, we call that the beginning of a micro avalanche, and we stop loading to separate all the events as best as we can. We let the avalanche dissipate, and when a lower limit is reached, we start loading again until we reach a second avalanche. You see the partitioning of the energies, and this is what we are seeing here is basically a zoom into two of these events. Okay. Here is a movie that shows this is basically one of the drops in a stress ratio, and this is the increase in the global kinetic energy, and this is the field of the kinetic energy that you are seeing here. You see lots of activities here. As a stress drops, you get a peak in the kinetic energy, and a micro avalanche happens in this range. I'll let it run once more. You see the event is happening here, then it dies out and it goes back to the background level. So we managed to separate all these micro avalanches. This is mostly done by Jordi. Essentially, what we are looking at are two ranges. This is the dense case, this is the loose case, and we are looking at ranges after the peak of stress for dense, when we start to see the events taking place, but before the steady state. And also we have another range B, which is much closer to a steady state. So if we go back to the critical state theory tells us that the state of the two material is the same only when the critical state or a steady state at the end is reached. The SES, however, if I go back to this picture, it tells us that the state is the same before the critical state, but when these two lines are aligned. So this is a little bit different. So basically, we are saying the state of these two material, they are basically, they should be very similar. They're both at a limit, and that's what we are seeing here. You see that the blue lines refer to the statistics of the drop in the elastic energy stored in the material and the kinetic energy. We have the blue lines for the loose cases and the red line for dense cases, and we see that it follows the same curve. So basically, the state of material is indistinguishable for the two cases, which is consistent with the prediction of the SES theory that I talked about. The exponent, we also looked at different exponent, and the main finding is what we have been looking for, that when this state is reached, we are dealing with a phase transition state, which is signified here by the power law distributions and exponents. So basically, here I'm reaching the end of my talk. We have seen that this concept of SES shows us it encompasses it basically includes the concept of critical state and yielding, and also it shows clear connection with a jamming transition that tells us when the material is becoming jammed or unjammed. One thing that I want to, so one other thing as a side note that we looked at is the correlation between the maximum values of stress for each event and the minimum ones, to see which one are better, can be used as a better reference. And we see that the autocorrelation function for top values are it gives us a more robust correlation. Means that if we go back here, the envelope encompassing the passing through the top values, the maximums of the event, is a better reference, and it is basically related to the concept of SES. And the minimums are basically arbitrary drops, and these are excursions that goes inside the jammed limit. And as a final note, so one topic that is very vexing in the engineering community of granular media is the rate dependency, and we don't know how critical state can be rate dependent. We don't have a good physics for it yet. But this topic, this idea of SES seems to show a good way to consider that, because if SES is the same as jamming limit, we already know that the jamming limit is also a function of temperature, and that can be related to the rate of loading, and that can directly give us the rate dependence. Okay, I'll stop my talk here. I ran a little bit, I think, over time, but I'll be at your disposal for any questions that you might have.
Thank you very much, Mehdi. We have a question by Kamran. Would you like Kamran to say it aloud? Or?
Thanks, Mehdi, for the interesting talk. So I'm curious about how this critical state theory, which was developed in the context of soil mechanics, how does that compare with the self-organized criticality? And I mean, both seem to be related in the sense that they both correspond to absorbing states, like in the phase space parameter, regardless of initial conditions. So
yes, yes. At the beginning, they appear to be very similar, but and it's misleading because one is called criticality, the other one is called critical state. But these things are quite different, because this concept of SES actually shows us what is different about it. You can see that this limit, this line, if the state of material is on that line, it is at the jamming limit, more or less. But critical state is only one point there. Critical state, as explained in critical state theory, is just one limit there. Or if we compare with the jamming, let me bring up one of these. So basically, critical state theory gives you one stress ratio at critical state, but your sample can be jammed or unjammed at different stress levels. So this one seems to be more general.
Okay.
Is there any other question? Or also any other question related to the talk by Kamran? So Mehdi, which are the next steps that you plan to tackle in this topic? Which are the open questions that you would like to address?
Oh, well, these data that we got from these simulations, they are very confusing to us for now, because this is not the only thing that we are looking at. For instance, we see very different behaviors in if you start looking really deep into each single micro avalanche and their behaviors, you can separate them to different categories and for instance, if it's dilating or contracting, they show different exponents, and we don't know really what. So we are trying to explain those things. And one other thing is this last one that I mentioned, but I have not done yet, is to exploit the already developed concept of jamming and the temperature dependency, turn it into rate dependency in critical state theory.
Also, thank you very much, Mehdi. Thank you again to Kamran. So I hope that you have enjoyed as much as me this last session of today. Tomorrow we will start again at 2 p.m. European time. And I wish you a good evening or good day, depending on your time zone. See you tomorrow then.
Thanks. Ciao.
Thank you very much.
Thank
See you tomorrow. Thank you, Kamran and Mehdi.
No problem, George.